You are moving through space at 670,000 miles per hour right now, and you cannot feel it. Your body, your home, your entire planet, the sun itself, all hurtling through the void, faster than anything humans have ever built. We are passengers on a cosmic conveyor belt, circling the center of a galaxy so vast that light itself needs 100,000 years just to cross it. 400 billion stars, spiral arms stretching farther than comprehension allows, a structure so enormous that for most of human history we believed it was everything. We called it the universe. We were wrong by a scale so staggering that the words to describe it barely exist. Because the Milky Way is not the universe, it is not even close. It is a single grain of sand in an ocean of 2 trillion galaxies. 2 trillion separate islands of stars, each one containing billions or trillions of suns, scattered across a volume of space 93 billion light-years wide. And that is only what we can see. The true universe, the one beyond the horizon of light and time, may be 250 times larger than everything our most powerful telescopes will ever touch. Right now, at this exact moment, galaxies are racing away from us so fast that their light will never reach Earth. Not in a billion years, not ever. They are being pulled beyond the edge of forever by a force we still do not understand, a mysterious pressure woven into the fabric of space itself. And the deeper we look, the smaller we become. This is the story of that shrinking, of how a galaxy that feels infinite measures almost nothing, and what it means to exist in a cosmos this impossibly, brutally, beautifully vast. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. You live on a rock, traveling at 828,000 kilometers per hour through a spiral of 400 billion suns, and you cannot feel it. Not a tremor, not a whisper, not the faintest hint that beneath your feet the ground is screaming through space faster than any vehicle humanity has ever built. Right now, while you watch this, the Earth is orbiting the Sun at about 107,000 kilometers per hour. The Sun, dragging the entire solar system with it, is orbiting the center of the Milky Way at roughly 515,000 miles per hour. And the Milky Way itself is falling through space toward Andromeda at about 250,000 miles per hour. You are moving through the cosmos at speeds that would make a fighter jet look like a parked car, and you have never once felt the wind. That says something uncomfortable about human perception. We built our understanding of the universe on what we can see and touch and measure with instruments barely more sophisticated than our own senses. And for most of history, that was fine. The sky looked fixed, the stars looked permanent, the ground beneath us felt solid and still. Then we did the math, and the math told us we were wrong about almost everything. The Milky Way is not small. Let's start there, because the temptation in a video like this is to skip straight to the part where we shrink everything down and make you feel insignificant. We will get there, but first, you need to understand what we are shrinking from. The Milky Way is a barred spiral galaxy roughly 100,000 light-years across. Some newer measurements push that number higher, closer to 150,000 or even 200,000 light-years, depending on what you count as the edge. A light-year, for anyone keeping score, is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, which means in a single year it covers about 9.46 trillion kilometers. Multiply that by 100,000 and you have the width of our galaxy. That is not a number your brain can hold. It is not supposed to be. Inside that 100,000 light-year disk, there are somewhere between 100 billion and 400 billion stars. The range exists because counting stars in a galaxy is harder than it sounds. You cannot see most of them. Dust blocks the view. Distance makes them too faint. Some are hidden behind other stars. Some are so dim they barely register at all. So astronomers estimate, they model, they extrapolate from what they can see and assume the rest follows similar rules. The current best guess sits around 400 billion. Picture that for a second. 400 billion stars, each one a sun, many of them larger than ours, some of them smaller, some burning alone, some in binary pairs, locked in mutual orbit, some surrounded by planets, some already dead, collapsed into white dwarfs or neutron stars or black holes, and all of it spinning together in a flat rotating disk held together by gravity and something we still do not fully understand, called dark matter. Our Sun sits about 26,000 to 28,000 light-years from the center of the Milky Way. Not in the core, where the density is highest and the radiation would sterilize anything trying to evolve. Not in the outer halo, where stars are sparse and metals are rare. Right in the middle band of the galactic suburbs, a comfortable distance, quiet, stable, unremarkable. The Sun orbits the galactic center once every 230 million years. Astronomers call that a galactic year. The last time the Sun was in this position in its orbit, the most advanced life on Earth was early dinosaurs. The time before that, insects were just learning to fly. The time before that, nothing on land had a backbone yet. One orbit, 230 million years. The Sun has completed that trip roughly 20 times since it formed 6 billion years ago. You are living on a world that is on its 20th lap around a spiral of suns so vast that light itself takes 100,000 years to cross it. Let's try to make that scale feel real, because numbers alone do not do it. If you shrunk the Milky Way down so that the Sun was the size of a grain of sand, the galaxy would still be wider than the continental United States. Every grain of sand in that model would be a star, and most of those grains would be separated by distances of several meters or more. Space, even inside a galaxy, is overwhelmingly empty. The stars are not packed together like marbles in a jar. They are scattered, isolated, drifting through oceans of vacuum so vast that even light, the fastest thing in the universe, takes years to travel from one to the next. Another way to think about it: if the Milky Way were a city, the Sun would be a single street lamp in a suburb about 3/4 of the way out from downtown. You could walk the diameter of that city at a steady pace, and it would take you 100,000 years, one step per year, 1 light year per step. You would pass 400 billion street lamps along the way. Most of them you would never notice. They would be too far off the path, too dim, hidden behind dust or distance. You would walk in silence for millennia at a time, the space between lights so vast that the glow of one fades long before the next appears. And at the center of that city, where the density is highest, there would be something that should not exist. A supermassive black hole weighing about 4 million times the mass of the Sun. We call it Sagittarius, a star. It sits at the exact gravitational center of the galaxy, and every star in the Milky Way, including ours, is in orbit around it. We have pictures of it now. In 2022, the Event Horizon Telescope, a network of radio dishes scattered across the planet working together as a single Earth-sized instrument, released the first direct image of Sagittarius, a star's shadow. It looks like a blurry orange donut. That donut is the glowing gas swirling around the black hole's event horizon, heated to millions of degrees before it falls in and vanishes forever. The black hole itself is invisible. It does not emit light. It does not reflect light. It is a hole in space where the rules stop working. And it is holding our galaxy together. The Milky Way is not a static structure. It is rotating. The inner regions spin faster than the outer regions, but not by much. In fact, the rotation curve of the Milky Way is one of the reasons we know dark matter exists. If the galaxy were made only of the matter we can see, stars, gas, planets, dust, then the outer edges should be rotating much slower than they are. The math does not work. The only way to make the numbers fit is to assume there is a vast halo of invisible mass surrounding the galaxy, pulling on everything with its gravity but emitting no light. We call it dark matter. We do not know what it is. We cannot see it. We have never directly detected it. But without it, galaxies like ours would fly apart. The stars on the outer edges would drift away into the void. The spiral arms would unwind. The whole structure would collapse or disperse within a few 100 million years. Dark matter is the scaffolding. The visible matter, everything we can see and touch and measure, is just the decoration. So when you picture the Milky Way, do not picture a flat disk of stars floating in empty space. Picture a massive sphere of invisible mass with a thin layer of visible matter embedded inside it. The stars and gas we see are only about 15% of the total mass. The rest is dark, hidden, holding everything together from the shadows. We live inside a structure we can only see a fraction of. The rest we infer from the way things move. Here is another number that will not fit in your head. The Milky Way contains roughly as much mass as 5 trillion suns. Most of that is dark matter. About 200 billion solar masses worth is in stars. Another 100 billion or so is in gas, dust, planets, black holes, neutron stars, and everything else. Add it all together, and you get a galaxy that weighs more than 1 trillion suns. And it is moving, the whole thing, all 5 trillion solar masses of it, falling through space at 250,000 miles per hour toward a neighboring galaxy that weighs about twice as much. But we will get to that. For now, the point is this. The Milky Way is not small, it is not modest. It is a structure so large that light itself, moving faster than anything else in the universe, takes 100,000 years to cross it. It contains hundreds of billions of stars, trillions of planets, more mass than 1 trillion suns, and it has been rotating, evolving, forming new stars and swallowing old ones for more than 13 billion years. If you were standing outside it, looking back, it would be one of the most striking objects in the sky. A brilliant spiral of light and dust, arms curling outward in a slow, elegant rotation. Beautiful, vast, impossible to take in all at once, and it is nothing. That is not an exaggeration. That is not narrative flourish. The Milky Way, for all its size and complexity, is a single galaxy in a universe that contains roughly 2 trillion of them. It is a droplet in an ocean, a grain of sand on a beach that stretches farther than light has had time to travel since the universe began. And the truly uncomfortable part is that we only figured this out recently. For most of human history, we did not even know other galaxies existed. In the early 1900s, the Milky Way was the universe. Astronomers knew it was big. They could see the band of light stretching across the sky, and they understood it was made of stars, but they assumed that was all there was. A single great island of stars, surrounded by infinite empty darkness. Then in 1924, Edwin Hubble, the man the space telescope is named after, used the 100-inch Hooker telescope on Mount Wilson in California to observe a fuzzy patch of light in the constellation Andromeda. Astronomers at the time called it the Andromeda Nebula and assumed it was a cloud of gas somewhere inside the Milky Way. Hubble found a type of star inside it called a Cepheid variable. These stars pulse at a rate that is directly tied to their true brightness. Measure the pulse, calculate the brightness, compare it to how bright the star looks from Earth, and you have a distance. Hubble did the math, and the number he got was staggering. The Andromeda Nebula was not inside the Milky Way. It was not even close. It was sitting more than 2 million light-years away, a separate galaxy, as large as our own. Maybe larger, and suddenly the universe was not one island anymore. It was an ocean. The Milky Way sits in what astronomers call the local group. That is not a poetic name, it is a literal description. The local group is a collection of roughly 50 galaxies that are gravitationally bound to each other. They are close enough that their mutual gravity keeps them together, prevents them from being pulled away by the expansion of space. The Milky Way is one of the two dominant members of this group. The other is Andromeda. Everything else in the local group is smaller, dwarf galaxies, irregular blobs of stars, satellite galaxies orbiting the larger ones like moons around a planet. Some of them you can see with the naked eye from the southern hemisphere. The Large Magellanic Cloud and the Small Magellanic Cloud are two of the Milky Way's satellite galaxies. They orbit us the same way we orbit the galactic center. They are small, maybe 10 billion stars each. But they are close enough and bright enough to show up in a dark sky as faint smudges. The local group spans about 10 million light-years across. That is 100 times the width of the Milky Way. And inside that volume, there are roughly 50 galaxies. Most of them are tiny. Most of them are dim. Most of them you would never notice unless you pointed a telescope directly at them. But they are there, and they are all moving, orbiting, falling toward each other, colliding in some cases. The local group is not a static snapshot. It is a dynamic system held together by gravity and filled with objects that have been interacting for billions of years. The Milky Way is not even the largest member of this group. Andromeda is. Andromeda, also called Messier 31, is a spiral galaxy roughly 220,000 light-years across, more than twice the width of the Milky Way, depending on whose measurement you trust. It contains roughly 1 trillion stars, maybe more. It is older, heavier, brighter, and it is coming toward us at about 250,000 miles per hour. The two galaxies are going to collide, not soon, not in any time frame that matters to human civilization. But in about 4 billion years, the Milky Way and Andromeda will merge into a single enormous elliptical galaxy that astronomers have already nicknamed Milkomeda. When that happens, the night sky will look different. Andromeda will grow larger and larger over millions of years until it fills half the sky. Stars will be flung out of their orbits. Some will be ejected from the merged galaxy entirely. Others will spiral inward toward the center. The supermassive black holes at the cores of both galaxies will eventually merge into a single black hole weighing roughly 10 million solar masses. And through all of that chaos, the Sun and Earth will probably survive. Probably. Galaxies are mostly empty space. The odds of the Sun actually colliding with another star during the merger are astronomically small. But the solar system's orbit will be disrupted. We might get flung into the outer halo. We might get pulled closer to the core. We might get ejected entirely, thrown out into intergalactic space as a rogue star system with no galaxy to call home. None of that matters to us now, but it is happening. The collision is already in progress. It is just moving slowly, That is the scale we are starting from. A galaxy 100,000 light-years wide, containing 400 billion stars. A solar system orbiting that galaxy once every 230 million years. A local group of 50 galaxies spanning 10 million light-years. And a neighboring galaxy twice our size heading toward us at 250,000 miles per hour. That is home. That is the neighborhood. That is the baseline. And if this were the full picture, it would already be overwhelming. But this is not the full picture. This is not even close. The local group is not alone. It is not special. It is not unusual. It is one small cluster in a universe that contains billions of clusters, and those clusters are themselves organized into larger structures. And those structures are woven into a cosmic web so vast that the Milky Way, for all its size and grandeur, is less than a speck of dust in a sandstorm. We thought we lived in the universe. We were wrong. We live in a corner of a suburb, in one galaxy, in one small group, in one supercluster, in one thread of a web that stretches across 93 billion light-years, and even that might not be the edge. We just established that the Milky Way is enormous. Hundreds of billions of stars spread across 100,000 light-years of rotating spiral. A structure so massive that light itself takes a human lifetime times 1,000 just to cross it. And now we need to talk about the thing that makes the Milky Way look small. Andromeda is coming, not metaphorically, not eventually, in some distant abstract future that doesn't concern us. Right now, tonight, while you sleep, while you work, while you go about your life, pretending the ground beneath you is stable and the sky above you is fixed. Andromeda, the largest galaxy in our neighborhood, is screaming toward the Milky Way at 250,000 miles per hour, and there is nothing anyone can do to stop it. Let's start with what Andromeda actually is, because for most of human history, we had no idea. If you go outside on a dark night far from city lights, away from the glow of street lamps and highways, and you look up toward the constellation Andromeda, you can see it, a faint smudge of light, dim, easy to miss. Most people who notice it assume it's a cloud or a distant star cluster. It is neither. What you are seeing with your naked eye is the combined light of roughly 1 trillion stars sitting 2.5 million light-years away. The photons hitting your retina left Andromeda before humans existed, before our ancestors came down from the trees, before anything on Earth had learned to use fire or language or tools. The light you are seeing tonight is older than our species. For centuries, astronomers catalogued Andromeda as a nebula, a cloud of gas somewhere inside the Milky Way, beautiful but unremarkable. Then, in 1924, Edwin Hubble pointed the 100-inch Hooker telescope at that faint smudge and found something that changed everything. He identified a type of star called a Cepheid variable, a star that pulses at a rate directly tied to how bright it truly is. By measuring the pulse and comparing it to how dim the star appeared from Earth, Hubble calculated the distance. The number he got was so large that it didn't fit inside the boundaries of the known universe. Andromeda wasn't a nebula. It wasn't inside the Milky Way. It was a separate galaxy. An island of stars, just as vast as our own, sitting more than 2 million light-years away in the darkness beyond. That single observation doubled the size of the universe overnight. Suddenly, we were not alone. The Milky Way was not the cosmos. It was one galaxy among many, and the closest one, the one we could see with our own eyes on a clear night, was Andromeda. Andromeda is bigger than us. That needs to be said plainly, because there is a tendency when talking about galaxies to treat them all as roughly equivalent. They are not. Andromeda is a giant. Its visible disk stretches about 220,000 light-years across, more than twice the width of the Milky Way, depending on whose measurement you trust. Some estimates are more conservative, closer to 150,000 light-years, but even the lower number makes Andromeda significantly larger than our galaxy. It contains about 1 trillion stars. The Milky Way has maybe 400 billion. Andromeda has more than twice that. More mass, more light, more gravity. If the local group were a neighborhood, Andromeda would be the biggest house on the block. It is also older. The stars in Andromeda's central bulge are ancient. Some of them formed more than 10 billion years ago, when the universe itself was still young. The galaxy has had time to grow, time to accumulate mass, time to consume smaller galaxies and add their stars to its own collection, and it shows. Andromeda's core is dense and bright, packed with old yellow and red stars that have been burning for billions of years. Its spiral arms are still actively forming new stars, but the bulk of its mass is old, mature, settled. The Milky Way, by comparison, is still in its prime, still forming stars at a steady rate, still growing. Andromeda has already done most of its growing. It is what the Milky Way will look like in a few billion years if it gets the chance to age gracefully. It will not get that chance. Here is what we know. Andromeda is moving toward the Milky Way at roughly 250,000 miles per hour. That is about 110 kilometers per second. For context, the fastest human-made object ever built, the Parker Solar Probe, maxes out at about 430,000 miles per hour when it is diving toward the Sun. Andromeda is moving at more than half that speed, and it is not a probe. It is a galaxy, 1 trillion stars, a mass equivalent to about 1.5 trillion suns, all of it falling toward us through the vacuum of space. The two galaxies are going to collide, not soon, not in any time frame that matters to anyone alive today, or their children, or their children's children, for 1,000 generations, but it is going to happen. Current estimates put the first close encounter somewhere between 2 and 3 billion years from now. Some models push it out to 4 billion. Some bring it in closer to 2. The range exists because predicting the exact trajectory of two massive rotating objects separated by 2.5 million light-years and influenced by the gravity of dozens of smaller galaxies in between is not simple, but every model agrees on the outcome. The Milky Way and Andromeda are going to merge. Let's walk through what that actually means, because the word collision gives the wrong impression. When two galaxies collide, stars do not smash into each other like cars in a highway pileup. Galaxies are mostly empty space. The stars inside them are separated by distances so vast that even during a merger, the odds of any two stars actually hitting each other are close to zero. You could fire the Sun like a bullet through the heart of Andromeda, and it would probably pass through without coming within a light year of another star. Space is big, stars are small. The math does not favor collisions. What does happen is gravity. As the two galaxies approach each other, their gravitational fields begin to interact. The outer edges of both galaxies start to distort. Stars get pulled out of their normal orbits. Long tidal tails of stars and gas stretch outward from both galaxies, drawn out by the gravitational tug-of-war. The spiral arms, once clean and symmetrical, begin to warp and tangle. Gas clouds that were stable and quiet get compressed by the encounter, triggering bursts of new star formation. Massive blue stars ignite across both galaxies, burning hot and fast before dying in supernova explosions that light up the night sky. From a distance, the collision would look like two glowing spirals slowly interpenetrating, their arms wrapping around each other, their cores drawing closer with each pass. The first encounter will not be the last. The two galaxies will pass through each other, their gravity pulling and stretching, but not enough to stop. They will separate again, moving apart for hundreds of millions of years. Then gravity will pull them back. A second pass, closer this time, more violent. More stars flung out into intergalactic space, more gas compressed into new star-forming regions. The spiral structures that took billions of years to develop will be shredded. After the second or third pass, the galaxies will no longer look like spirals. They will look like chaos. Streams of stars arcing through space, dense clumps of gas collapsing into clusters of newborn suns. And at the center of it all, two supermassive black holes, each weighing millions of times the mass of the Sun, spiraling toward each other. Eventually, maybe a billion years after the first encounter, the two galaxies will settle. The chaotic tangle of stars will collapse into a single merged structure. Most models predict the result will be a giant elliptical galaxy. No spiral arms, no flat rotating disk. Just a massive, roughly spherical cloud of stars, slowly rotating, filled with old red and yellow stars, and scattered with the remnants of the star-forming regions that ignited during the collision. Astronomers have already given it a name, Milky, a combination of Milky Way and Andromeda. It is not official, it is not formal, but it has stuck. Milky will be one of the largest galaxies in the local group. It will contain roughly 1.4 trillion stars. It will span hundreds of thousands of light years. And sitting at its core will be a single supermassive black hole weighing about 10 million solar masses, the product of the merger between the black holes currently sitting at the centers of the Milky Way and Andromeda. That black hole will be surrounded by a dense cluster of old stars, packed so tightly that the night sky from a planet in that region would be filled with thousands of visible stars, far brighter than anything we see from Earth. And somewhere in that merged galaxy, if it survives, will be our solar system. The Sun, the Earth, the planets. All of it still orbiting the center, just in a very different orbit than the one we are in now. There is a chance, a real possibility, that the solar system gets flung out of the galaxy entirely during one of the merger passes. Ejected into intergalactic space as a rogue star system, no longer bound to any galaxy. If that happens, the night sky will go dark. The Milky Way, the glowing band of light that has defined human understanding of the cosmos for millennia, will shrink to a faint smudge in the distance. Andromeda will do the same in the opposite direction. And the sky above Earth will be black except for the planets and the handful of stars that got ejected along with us. It would be the loneliest sky imaginable. An entire galaxy of stars visible in the distance but unreachable forever. If the solar system stays inside the merged galaxy, the night sky will look different but not empty. Andromeda, which currently appears as a faint smudge, will grow larger over millions of years, slowly at first, then faster. By the time the first close encounter happens, Andromeda will fill a quarter of the sky. A glowing spiral stretched across the heavens, its arms visible in detail, its core blazing with the light of 100 billion stars. It will be the most dramatic sight in the history of Earth's sky, assuming anything on Earth is still around to see it. The Sun will still have a few billion years of stable burning left at that point, but whether Earth remains habitable is another question. The increasing luminosity of the Sun over billions of years will eventually boil away the oceans and turn the planet into a lifeless desert long before the Milky Way and Andromeda finish merging. So the most spectacular sky in Earth's history will probably play out over a dead world, no audience. No witnesses, just physics doing what physics does. Through all of this, the odds of the Sun actually colliding with another star remain absurdly low. Galaxies are so sparse that even during a direct merger, the stars mostly miss each other. But the Sun's orbit will change. Right now, the Sun sits in a stable, nearly circular orbit about 26,000 light-years from the galactic center. After the merger, that orbit could become elliptical. We could get pulled closer to the core. We could get flung outward into the halo. We could get tossed out entirely. All of that is possible. None of it is predictable with enough precision to say for certain what will happen. The best models give probabilities. Most of them agree that the Sun will stay inside the merged galaxy. A few say we might get ejected. None of them say we are doomed. Stars survive galactic mergers all the time. The Milky Way itself has already consumed dozens of smaller galaxies over its lifetime, and those stars are still here, orbiting the center along with everything else. The Andromeda collision is not unique. Galactic mergers happen constantly throughout the universe. We see them in progress in telescopes all the time. Galaxies tangled together, their arms stretched into long filaments, their cores glowing brightly as compressed gas ignites into new stars. Some of the most famous images from the Hubble Space Telescope show galaxies in mid-collision, the antennae galaxies. The Whirlpool Galaxy slowly consuming a smaller companion. The Mice Galaxies, named for the long tails of stars streaming away from them. All of these are snapshots of what the Milky Way and Andromeda will look like in a few billion years. Violent, chaotic, beautiful, and ultimately temporary. Every merger ends the same way. A single larger galaxy, a denser core, a scattered halo of stars. The details change, but the outcome is always the same. Two become one, and that brings us to the larger context, because the Milky Way and Andromeda are not alone. They are the two largest members of a small collection of galaxies called the local group. And understanding the local group is the first step toward understanding just how small our corner of the universe really is. The local group is a gravitationally bound cluster of galaxies. That means the galaxies inside it are close enough that their mutual gravity holds them together. They are not being pulled apart by the expansion of the universe the way more distant galaxies are. They are a family, a neighborhood, a small island of galaxies that will stay together, more or less, for the lifetime of the cosmos. The local group spans about 10 million light-years from edge to edge. That is 100 times the width of the Milky Way. Inside that volume, there are somewhere between 40 and 100 galaxies depending on who is counting and where they draw the boundary. Most of those galaxies are tiny, dwarf galaxies, irregular blobs of a few billion stars. Some of them barely qualify as galaxies at all. They are more like large star clusters that happen to have their own gravity. The three dominant members of the local group are the Milky Way, Andromeda, and a smaller spiral galaxy called Triangulum, also known as Messier 33. Triangulum sits about 3 million light-years away and contains roughly 40 billion stars. It is the third largest galaxy in the local group, but it is dwarfed by both the Milky Way and Andromeda. Triangulum is also being pulled toward Andromeda, and some models suggest it will eventually merge with Andromeda, either before or during the Milky Way collision. If that happens, Milkomeda will be even larger, incorporating Triangulum's stars along with everything else. The rest of the local group is made up of satellite galaxies, small companions that orbit the larger ones like moons around a planet. The Milky Way has dozens of these satellites. The most famous are the Large Magellanic Cloud and the Small Magellanic Cloud, both visible to the naked eye from the southern hemisphere. Each of these dwarf galaxies contains a few billion stars. They are being slowly torn apart by the Milky Way's gravity, and in a few billion years they will be absorbed completely. Andromeda has its own collection of satellites, maybe 20 or 30, depending on the count. Some of them are faint smudges, barely detectable, even with modern telescopes. Others are relatively bright, at least by dwarf galaxy standards. The local group is not special. It is not unusually large or unusually dense. It is a fairly typical small cluster of galaxies. There are thousands of groups like it scattered across the universe. Some are smaller, some are larger. Most contain a few large galaxies and a swarm of smaller ones. The local group happens to be ours. It is home, and in the grand scheme of the cosmos, it is almost invisible. Here is the uncomfortable part. The local group, for all its size, is nothing. 10 million light-years sounds enormous. It is enormous by any human measure. But step back far enough, and the local group shrinks to a dot, a single point of light in a much larger structure. Because the local group is not alone. It sits inside a much larger collection of galaxy groups and clusters called the Virgo Supercluster, which itself is just one small thread in a cosmic web that spans the entire observable universe. The Milky Way and Andromeda and all their satellite galaxies are a footnote, a minor detail in a structure so vast that the human brain cannot hold it. We thought the Milky Way was the universe. Then we found Andromeda. Then we found the local group. Then we found the supercluster. And every time we zoomed out, the scale grew by a factor of 100 or 1,000. Every time we thought we had reached the edge, we found something larger waiting beyond it. The Milky Way is not the cosmos. It is not the neighborhood. It is not even the street. It is one house on one block, in one suburb, of a city so large that light itself has not had time to cross it since the universe began, and we are only getting started. We just established that the local group is home. 10 million light-years of gravitationally bound galaxies, the Milky Way, Andromeda, Triangulum, and a few dozen smaller companions all orbiting each other in a slow cosmic dance that will eventually end in a merger. For most of human history, discovering that we lived in a group of galaxies would have been the end of the story. The final zoom out, the ultimate scale. We found the neighborhood, mapped its boundaries, counted its members, and that was supposed to be enough. It was not even close. The local group is not alone. It sits inside something much larger, and that larger thing sits inside something even bigger. And the hierarchy keeps going, structure nested inside structure, each level 100 times the scale of the one before it, until you reach distances so vast that light itself has not had time to cross them since the universe began. The first hint that the local group was part of something bigger came in the 1950s when astronomers started mapping the positions of nearby galaxies in 3 dimensions. They expected to find galaxies scattered more or less randomly across space, the way stars are scattered across the sky. A few clumps here and there, sure, but mostly uniform. That is not what they found. Galaxies were concentrated, packed into dense regions, separated by vast stretches of emptiness. The universe was not smooth. It was lumpy, clustered, organized into structures that had no business existing unless gravity had been pulling things together for billions of years. The nearest of these concentrations sits about 54 to 65 million light-years away, depending on whose measurement you trust. It is called the Virgo cluster, named after the constellation where it appears in our sky. And it is the first structure beyond the local group that makes the Milky Way look truly insignificant. The Virgo cluster contains somewhere between 1,300 and 2,000 galaxies. Let that number sit for a second. Not 50 galaxies like the local group, not a few hundred. At least 1,300. Some estimates push the count closer to 2,000 if you include the faintest dwarf galaxies scattered around the edges. Most of those galaxies are small, dwarfs and irregulars containing a few billion stars each, but scattered among them are giants, massive elliptical galaxies weighing trillions of solar masses. Galaxies so large they make Andromeda look modest. And all of them are packed into a region roughly 15 million light-years across. That is only 50% wider than the local group, but it contains 40 times as many galaxies. The density is staggering. If the local group is a quiet suburban neighborhood, the Virgo cluster is downtown Manhattan at rush hour. At the center of the Virgo cluster sits a galaxy called Messier 87, or M87 for short. You might have heard of it. In 2019, the Event Horizon Telescope released the first direct image of a black hole's shadow, and that black hole was sitting at the heart of M87. The black hole weighs about 5 billion solar masses. For context, the black hole at the center of the Milky Way weighs about 4 million. The one in M87 is more than 1,500 times heavier, and the galaxy surrounding it is proportionally massive. M87 is a giant elliptical galaxy containing roughly 1 trillion stars. It spans about 240,000 light-years across, making it slightly larger than Andromeda. But unlike Andromeda, which is a spiral with active star formation and a relatively young stellar population, M87 is old, ancient. Its stars are predominantly red and yellow giants that have been burning for billions of years. The galaxy stopped forming new stars long ago. It has settled into a kind of cosmic retirement, slowly growing by cannibalizing smaller galaxies that wander too close. M87 sits at the gravitational center of the Virgo cluster. Every galaxy in the cluster is orbiting it. Some are moving quickly, whipping past at speeds of thousands of kilometers per second. Others are drifting slowly inward, caught in M87's gravity well, doomed to merge with it over the next few billion years. The cluster is not a static arrangement, it is a dynamic system. Galaxies collide, merge, get torn apart by tidal forces. Gas gets stripped from smaller galaxies by the hot plasma that fills the space between them. Over billions of years, the Virgo cluster will continue to consolidate. The number of galaxies will drop as they merge into larger and larger objects. Eventually, in the far future, the cluster might collapse into a single supergiant elliptical galaxy containing the combined mass of everything that once orbited M87. That process is already underway. We are just watching it happen in slow motion. The Virgo cluster is not unique. It is one of thousands of similar clusters scattered across the observable universe. Some are smaller, some are much larger. The Coma cluster, sitting about 300 million light-years away, contains more than 1,000 large galaxies and thousands of smaller ones. The Fornax cluster, closer at about 60 million light-years, contains roughly 350 galaxies. Clusters are a common feature of the universe. Anywhere you point a telescope and look deep enough, you will find them. Concentrations of galaxies packed together by gravity, surrounded by vast regions of emptiness. For a long time, astronomers assumed clusters were the largest structures in the universe. They thought the hierarchy stopped there. Galaxies formed groups, groups formed clusters, clusters were scattered randomly across space. End of story. Then they started mapping the three-dimensional positions of clusters, and they found something that should not have been possible. Clusters were not randomly distributed. They were organized, aligned. strung together in long filaments and sheets, separated by enormous voids where almost nothing existed. The universe, at the largest scales, looked less like a random scattering of points and more like a spider web, or a sponge, or a network of soap bubbles. Depending on who you asked, the metaphor changed, but the underlying structure was always the same. Clusters sat at the intersections of vast cosmic filaments. The filaments connected the clusters like highways between cities. And the voids, the empty regions between the filaments, stretched for hundreds of millions of light-years, with almost no galaxies inside them at all. This is where the concept of a supercluster comes in. A supercluster is not a single bound object, the way a galaxy or a cluster is. It is a large-scale structure, a region of space where clusters and groups are loosely associated, connected by the filaments of the cosmic web. The boundaries are fuzzy, the definition is somewhat arbitrary, but the scale is undeniable. Superclusters span hundreds of millions of light-years. They contain tens of thousands of galaxies, and they represent the largest coherent structures in the universe. The Milky Way sits inside a supercluster. For decades, astronomers called it the Virgo supercluster or the local supercluster. The idea was simple. The Virgo cluster sits at the center. The local group and dozens of other smaller groups and clusters orbit around it. The whole thing spans roughly 110 million light-years and contains about 47,000 galaxies. That was the model. That was what the textbooks said. Then in 2014, a team of astronomers led by Brent Tully at the University of Hawaii published a paper that redefined the boundaries completely. They were not looking at where galaxies were located. They were looking at where galaxies were moving. Using data from thousands of galaxies, they mapped the motion of everything in our local region of the universe. They traced the flow, and what they found was that the Virgo supercluster, as it had been traditionally defined, was too small. The gravitational influence extended much farther. The local group was not orbiting the Virgo cluster. It was part of a much larger structure, a vast basin of gravitational attraction that stretched across 400 million light-years and contained roughly 100,000 galaxies. They called it Laniakea. The name is Hawaiian. It means immense heaven, or open skies, depending on the translation. Either way, it fits. Laniakea is enormous. It is one of the largest structures ever identified in the universe, and it is home. The Milky Way, Andromeda, the local group, the Virgo cluster, all of it sits inside Laniakea. We are not orbiting the Virgo cluster. We are drifting through a much larger system. A supercluster so vast that even traveling at the speed of light, it would take 400 million years just to cross it. Let's try to make that scale real, because the numbers alone do not convey it. The Milky Way is 100,000 light-years across. The local group is 10 million light-years. The Virgo cluster is 15 million. Laniakea is 400 million. That is 4,000 times the width of the Milky Way. If you shrunk Laniakea down so that the Milky Way was the size of a grain of sand, the supercluster would stretch across several city blocks, and every other grain of sand in that space would be another galaxy, 100,000 of them, each one containing billions or trillions of stars, each one a world unto itself, and all of them drifting together through space, bound by gravity into a single immense structure that took billions of years to assemble. Laniakea is not a sphere. It is not a neat geometric shape. It is irregular, lumpy, stretched. If you could see it from the outside, it would look like a network of glowing filaments connecting dense nodes. The Virgo cluster is one of those nodes. There are others: the Hydra Centaurus supercluster, the Pavo Indus supercluster. each one a concentration of galaxies sitting at the intersection of filaments. The filaments themselves are made of galaxies and dark matter, stretched out in long threads across hundreds of millions of light years. And between the filaments are voids, enormous empty regions where galaxies are rare or absent entirely. The largest known void, the Bootes void, stretches about 330 million light-years across and contains only about 60 galaxies. For comparison, a typical region of space that size should contain thousands. The Bootes void is a hole, a gap in the cosmic web, where for reasons we still do not fully understand, galaxies never formed in significant numbers. The discovery of Laniakea changed the way astronomers think about the universe. It confirmed that structure exists at scales far larger than individual clusters. It showed that the motion of galaxies is not random. Everything is flowing, falling, drifting toward regions of higher density. Laniakea itself is moving. The entire supercluster, all 100,000 galaxies, is being pulled toward something even larger. Astronomers call it the Great Attractor. It is a gravitational anomaly sitting beyond the edge of Laniakea in a region of space obscured by the dust and stars of the Milky Way. We cannot see it directly, but we can measure its effect. Everything in our region of the universe, including Laniakea, is moving toward it at about 600 kilometers per second. The Great Attractor itself is not a single object. It is likely a concentration of mass, possibly another supercluster or a dense collection of clusters. And it too is being pulled by something farther out. The Shapley supercluster, one of the most massive concentrations of galaxies in the nearby universe, sits about 650 million light-years away and contains more than 8,000 galaxies. Its gravitational influence extends across billions of light-years. Everything in this corner of the cosmos is falling toward it, slowly, inexorably, pulled by gravity across distances so vast that even after billions of years we have barely moved. Here is what that means. The Milky Way is not drifting randomly through space. It is part of a flow, a current in the cosmic web. We are falling through the universe along with everything else in Laniakea, pulled by gravity toward regions of higher density. And Laniakea itself is falling toward the Shapley supercluster, and the Shapley supercluster is being pulled by structures even farther out. The universe is not static. It is not a photograph. It is a dynamic system. Everything is moving. Everything is falling. And the scales involved are so large that the motion is invisible to us. The Milky Way has been falling toward the Great Attractor for billions of years, and it will continue falling for billions more. We will never arrive. The expansion of the universe will eventually overcome the gravitational pull, and the distance between us and the Great Attractor will start growing instead of shrinking. But for now, we are falling. The cosmic web is the framework that organizes all of this. It is not a literal web made of threads. It is a pattern, a structure that emerges naturally from the way gravity works on the largest scales. After the Big Bang, the universe was not perfectly smooth. There were tiny fluctuations in density, regions where matter was slightly more concentrated than average. Over billions of years, those fluctuations grew. Gravity pulled matter toward the denser regions. The dense regions got denser. The less dense regions got emptier. Over time, the universe separated into filaments and voids. Matter collected along the filaments like beads on a string. Where filaments intersected, clusters formed. Where clusters were close together, superclusters emerged. The whole structure is held together by dark matter, the invisible scaffolding that makes up about 85% of the matter in the universe. We cannot see dark matter. We cannot detect it directly, but we can see its effect. The galaxies we observe are embedded in halos of dark matter. The filaments of the cosmic web are made mostly of dark matter. The voids are not truly empty. They contain dark matter too, just much less of it. Baryonic matter, the ordinary stuff that makes up stars and planets and people, follows the dark matter. It falls into the same gravitational wells, it collects in the same filaments, and it lights up when it collapses into stars, making the structure visible. The cosmic web is not theoretical. We have mapped it. The Sloan Digital Sky Survey, one of the largest astronomical surveys ever conducted, spent more than a decade mapping the positions and distances of millions of galaxies. The result is a three-dimensional map of the nearby universe, and when you look at that map, the web is unmistakable. Filaments stretch across hundreds of millions of light-years. Clusters sit at the intersections. Voids span enormous volumes. The structure repeats at every scale. Zoom in and you see groups of galaxies. Zoom out and you see clusters. Zoom out farther and you see superclusters. Zoom out even more and you see the web itself, stretching across billions of light-years. The pattern is fractal, self-similar, the same structure at every level. Here is the part that should bother you. The Milky Way, for all its size and grandeur, is invisible at this scale. If you pulled up the Sloan Digital Sky Survey map and zoomed out far enough to see Laniakea, the Milky Way would not show up. It would be lost in the noise. One galaxy among 100,000. A single point of light, too faint to register. The local group would be invisible too. Even the Virgo cluster, with its 1,300 galaxies, would just be a slightly brighter dot in a long filament of dots. The scale is so large that individual galaxies do not matter. They are the pixels, the atoms, the smallest units in a structure so vast that it makes everything we thought was enormous look trivial. And Laniakea is not special. It is not the largest supercluster. It is not the densest. It is not unique in any meaningful way. It is simply the one we happen to live in. There are thousands of superclusters scattered across the observable universe. Some are larger, some contain more galaxies. The Sloan Great Wall, a structure discovered in 2003, stretches about 1.38 billion light-years across. It is a vast sheet of galaxies, a wall in the cosmic web, and it is one of the largest structures ever observed. But it is not alone. The Hercules Corona Borealis Great Wall, discovered in 2013, might be even larger. Estimates put it at about 10 billion light-years across, though the exact size is still debated because defining the boundaries of such a massive structure is not straightforward. If that measurement holds, it would be the largest single structure in the known universe, a wall of galaxies so vast that light takes 10 billion years to cross it. That is more than 2/3 the age of the universe. It is so large that it challenges some of the assumptions of cosmology. The universe is supposed to look roughly the same in every direction at the largest scales. That is called the cosmological principle. A structure 10 billion light-years across pushes right up against the edge of what the principle allows. Any bigger and the universe would start to look lumpy at scales where it should be smooth. But even if the Hercules Corona Borealis Great Wall turns out to be smaller than initially thought, the point stands. Superclusters are everywhere. Laniakea is one of thousands, maybe tens of thousands. We do not know the exact count because we have not mapped the entire observable universe yet. We have mapped the nearby regions in detail. We have surveyed deep slices of the sky to see how structure changes with distance. But a complete three-dimensional map of every galaxy in the observable universe does not exist yet. It will take decades to build, maybe longer. The farther out you look, The fainter the galaxies get, the harder they are to detect, the more time you need on a telescope to measure their distances. Mapping the cosmic web is one of the great ongoing projects in astronomy. And every time we push the map a little farther, we find more of the same, more filaments, more clusters, more superclusters. The structure does not stop. The hierarchy is almost absurd when you write it out. Planets orbit stars. Stars orbit galactic centers. Galaxies cluster into groups. Groups cluster into clusters. Clusters connect into superclusters. Superclusters weave into the cosmic web. And the web itself spans the entire observable universe. Each level is roughly 100 times larger than the one below it. Each level contains 100 times more mass, and at each level, the previous scale becomes almost invisible. The Milky Way is enormous compared to the solar system, trivial compared to the local group, invisible compared to Laniakea. It is a matter of perspective, and the perspective keeps expanding. We thought the Milky Way was the universe. Then we found other galaxies. Then we found the local group. Then we found clusters. Then we found superclusters. Then we found the web. And every time we zoomed out, everything we thought was large became small. Everything we thought was significant became a footnote. The Milky Way is not the center. It is not special. It is not even particularly noticeable. It is one thread in a filament in a web that stretches farther than we can see. And that web, vast as it is only the beginning. Because even the cosmic web, even the superclusters, even the largest structures we have ever mapped, are just features inside something much, much larger. We just mapped the largest structures astronomers have ever identified. Superclusters stretching hundreds of millions of light-years across. Laniakea, our home supercluster, containing 100,000 galaxies spread across 400 million light-years. The Shapley supercluster, pulling everything in this corner of the universe toward it with gravitational influence that extends across billions of light-years. Structures so vast that individual galaxies become invisible. Structures so large they should not exist according to some interpretations of how the universe is supposed to look at the largest scales. And yet when you zoom out far enough, even those structures reveal themselves to be something smaller, not isolated objects floating in emptiness, not random concentrations of matter scattered across space. They are nodes, intersections, knots in a web that spans the entire observable universe. A web that has been growing for 13.8 billion years. A web that contains every galaxy, every star, every atom that has ever existed. And a web that, for all its complexity, follows a pattern so simple it almost feels like a trick. The cosmic web is not a metaphor. It is a literal description of what the universe looks like when you map it at the largest scales. Galaxies are not spread evenly across space the way you might scatter salt across a table. They are organized, threaded together in long filaments that stretch for hundreds of millions of light-years. Those filaments connect at dense intersections where galaxy clusters sit like cities at the convergence of highways. And between the filaments, separating them, filling most of the volume of the universe, are voids. Enormous empty regions where galaxies are rare or absent entirely. The universe, at its largest scale, looks less like a smooth distribution of matter and more like a sponge or a foam, or a network of soap bubbles stretched across billions of light-years. The metaphor changes depending on who is describing it, but the structure is always the same. Filaments, nodes, voids, repeating across the entire observable cosmos. The discovery of this structure was gradual. It was not a single observation or a single telescope. It was the slow accumulation of data over decades, as astronomers mapped the positions of more and more galaxies and started plotting them in 3 dimensions. In the 1980s, the first large redshift surveys began. A redshift survey measures how much the light from a galaxy has been stretched by the expansion of the universe. The more stretched the light, the farther away the galaxy is. By measuring the redshifts of thousands of galaxies, astronomers could calculate their distances and plot their positions in space. The results were shocking. Galaxies were not scattered randomly. They were concentrated along thin sheets and filaments. And between those concentrations were vast empty regions. One of the first voids ever identified was discovered in 1981 by astronomer Robert Kirshner and his team during a redshift survey of a region in the constellation Bootes. They were mapping galaxies, expecting to find a fairly uniform distribution. Instead, they found a hole. A vast region of space roughly 330 million light-years across that contained almost no galaxies at all. They counted about 60 galaxies in a volume where they should have found thousands. The region was not completely empty, but it was close. Close enough that it earned the name the Bootes Void, sometimes called the Great Void or the Great Nothing. A bubble in the cosmic web where, for reasons still not entirely understood, galaxies simply never formed in significant numbers. The Bootes Void was not an anomaly. Once astronomers knew what to look for, they started finding voids everywhere. The local void, sitting relatively close to the Milky Way, spans about 150 million light-years. The Capricornus Void, the Sculptor Void. The list kept growing. Voids, it turned out, are not rare. They are a fundamental feature of the universe. They occupy most of the volume. If you picked a random point in space, odds are it would be inside a void, not inside a filament or a cluster. The universe is mostly empty. The matter we see, the galaxies and stars and gas, is concentrated in a thin network of filaments and sheets that outline the voids like the edges of soap bubbles. Here is the scale you need to understand. The typical void spans about 100 to 300 million light-years across. Some are smaller, some are larger. The Bootes Void at 330 million light-years is on the larger end, but not the largest. The voids are not perfect spheres. They are irregular, lumpy, stretched, but they all share the same basic property. Very few galaxies inside. Most of the volume is just space, empty space, or at least space that looks empty. Because even in the voids, there is dark matter, there is some gas. There are a few scattered dwarf galaxies, but the density is so low that for practical purposes, the voids are vacant. The filaments are the opposite, dense, bright, packed with galaxies. A typical filament is a long, narrow structure stretching between galaxy clusters. The length can be hundreds of millions of light-years. The width is much smaller, maybe 10 to 20 million light-years across. Filaments are not solid objects. They are concentrations of galaxies and dark matter stretched out in long threads. If you could see a filament from the outside, it would look like a glowing highway, a river of galaxies flowing between clusters, and along that highway, matter is moving. Galaxies are falling inward along the filament, pulled by gravity toward the densest regions. The filaments act like channels. They funnel matter from the voids into the clusters. Over billions of years, the voids get emptier, and the clusters get denser. The web is not static, it is growing, evolving, collapsing inward along its own structure. The reason the universe looks like this, the reason we have filaments and voids instead of a smooth distribution of galaxies, comes down to gravity and time. After the Big Bang, the universe was not perfectly smooth. There were tiny fluctuations in density, regions where matter was slightly more concentrated than average. Those fluctuations were incredibly small, less than 1 part in 100,000, but they were there. And over billions of years, gravity amplified them. Matter in the denser regions pulled in more matter from the surrounding space. The dense regions got denser. The less dense regions got emptier. Over time, the universe separated into a network of high-density and low-density regions. The high-density regions collapsed into filaments and clusters. The low-density regions expanded into voids. Dark matter played the critical role in all of this. Dark matter makes up about 85% of the matter in the universe. It does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity, but it has mass, and mass creates gravity. In the early universe, dark matter was the first thing to start clumping. It fell into the densest regions and created gravitational wells. Ordinary matter, the gas that would eventually form stars and galaxies, followed. It fell into the same wells. It collected in the same filaments. And when it got dense enough, it collapsed into stars. The galaxies we see today are embedded in halos of dark matter. The filaments of the cosmic web are made mostly of dark matter. The voids contain dark matter too, just much less of it. The entire structure of the universe is scaffolded by dark matter. The visible matter, the stars and galaxies, are just tracing out the underlying dark matter framework. NASA describes the cosmic web as a structure where galaxies rest on empty bubbles, with bright knots representing galaxy clusters and purple filaments showing the connecting material. That is a useful way to picture it. Imagine a foam made of soap bubbles. The bubbles are the voids. The thin films where the bubbles meet are the filaments and sheets. The points where multiple films intersect are the clusters. That is the cosmic web, a foam of voids outlined by filaments, with clusters sitting at the densest intersections. And the whole thing spans the observable universe, 93 billion light-years from edge to edge, filled with roughly 2 trillion galaxies, all of them sitting somewhere on this web, all of them connected, at least loosely, by the filaments. The structure is not random. It follows patterns. Simulations of the cosmic web run on supercomputers using the known laws of physics and the known properties of dark matter reproduce the structure almost perfectly. You start with a smooth universe with tiny fluctuations in density. You let gravity run for 13.8 billion years. And what you get looks exactly like what we see through telescopes: filaments, clusters, voids. The match is so close that cosmologists consider the cosmic web to be one of the strongest pieces of evidence that our understanding of the universe, the standard model of cosmology, is correct. The model predicted the web before we had fully mapped it. The observations confirmed the prediction. That does not happen often in science. Here is what that means for scale. The Milky Way sits on a filament, a relatively minor one, but a filament nonetheless. That filament connects the local group to the Virgo cluster and extends outward into the larger structure of Laniakea. From the perspective of the cosmic web, the local group is a tiny knot on a thread. The Virgo cluster is a slightly larger knot. Laniakea is a small section of the web where several filaments intersect. And the entire supercluster, all 100,000 galaxies, is just one part of a much larger pattern that repeats across billions of light-years. Zoom in and you see the Milky Way. Zoom out and the Milky Way disappears. Zoom out farther and the local group disappears. Zoom out even more and Laniakea starts to look like a single thread in a much larger web. The hierarchy does not stop until you reach the scale of the observable universe itself. Let's talk about what it is like inside a void, because the voids are, in some ways, the most interesting part of the web. If you were somehow able to place yourself inside the Bootus void, 330 million light-years across, the night sky would look almost empty. There would be no Milky Way, no band of light stretching across the sky. The nearest galaxy might be tens of millions of light-years away, maybe farther. You would see a few faint smudges scattered across the darkness, distant galaxies sitting at the edges of the void, but most of the sky would be black, deep black. Blacker than anything you can see from Earth, because there would be no nearby stars to light up the foreground, no dust, no gas, just emptiness. If intelligent life somehow evolved on a planet inside a void, they would have a very different understanding of the universe than we do. They would look up and see almost nothing. For most of their history, they would have no idea galaxies existed. No idea there was anything beyond their own small island. They would be cosmically isolated in a way that is hard to imagine. The voids are not completely empty, though. There are some galaxies inside them, dwarf galaxies mostly, small irregular blobs of a few billion stars. These void galaxies are strange. They tend to be younger than galaxies in filaments or clusters. They have more gas. They are forming stars at a higher rate. The reason is environmental. Galaxies in clusters and filaments are constantly being disturbed. They collide with each other. They pass through hot gas that strips away their own gas reserves. They get tidally disrupted by the gravity of nearby galaxies. Life in a dense part of the web is violent. Life in a void is quiet. A void galaxy can sit undisturbed for billions of years, slowly forming stars, never merging with anything, never getting stripped or compressed. It is a different evolutionary path, and it produces different kinds of galaxies. The cosmic web is not a recent discovery, but it took a long time to map. The first hints came in the 1980s with redshift surveys like the CFA Redshift Survey and the survey that found the Bootus void. Those early surveys mapped a few thousand galaxies, enough to see the voids and filaments in rough outline. Then came larger surveys. The 2-degree field galaxy redshift survey in the late 1990s mapped more than 200,000 galaxies. The Sloan Digital Sky Survey, which began in 2000 and is still running in various forms, has mapped millions. Each new survey pushed the map farther out and filled in more detail. And every time, the structure got clearer, the web became more obvious, the voids grew sharper, the filaments more defined. The pattern held at every scale. One of the most striking visualizations of the cosmic web comes from a simulation called Illustris, run in 2014. Illustris is not a real observation, it is a computer model, a simulation of how the universe evolves from the Big Bang to the present day. The simulation starts with the known conditions of the early universe: tiny fluctuations in density, dark matter, ordinary matter, radiation, expansion. Then it runs the physics forward for 8 billion years. The result is a cube of simulated space, 350 million light-years on a side, filled with galaxies, clusters, filaments and voids. And when you look at the output, it looks exactly like the real universe. The filaments are there, the voids are there, the clusters sit at the intersections. The match is so precise that astronomers use simulations like Illustris to test their understanding of galaxy formation and cosmic structure. If the simulation matches reality, the physics is probably correct. If it does not, something is missing. Here is the thing that should unsettle you. The cosmic web is not being held together by anything. The filaments are not strings. The voids are not bubbles with walls. The web is a transient structure. It exists because gravity is pulling everything together, and the expansion of the universe is pulling everything apart, and the balance between those two forces creates the pattern we see. But that balance is shifting. The universe is expanding faster now than it was a few billion years ago. Dark energy, whatever it is accelerating the expansion. Over time, the filaments will start to stretch, the voids will grow larger, the clusters will become more isolated. Eventually, trillions of years from now, the web will dissolve, the filaments will break apart, the clusters will drift away from each other, and the universe will become a cold, dark, empty expanse with isolated islands of galaxies separated by distances so vast that light from one will never reach another. The cosmic web is temporary. It is a feature of this epoch of the universe, a pattern that only exists because we happen to be living at a time when gravity and expansion are roughly balanced. In the deep future, there will be no web, just isolation. But we are not there yet. Right now, the web is growing, collapsing inward along its own structure. Galaxies are falling along filaments into clusters. Clusters are merging into larger clusters. The voids are expanding as matter drains out of them into the filaments. The process is slow. It takes billions of years for a galaxy to fall from the edge of a void into a filament, but it is happening. The universe is becoming clumpier, more structured. The web is tightening, and it will continue to tighten for a long time before dark energy finally wins and starts pulling it apart. The scale of the web is difficult to process because it operates at timescales and distances that human brains are not built to comprehend. A filament stretching 500 million light-years is not just a big thing. It is a thing so large that light from one end takes 500 million years to reach the other. The universe was a very different place 500 million years ago. There were fewer heavy elements, fewer rocky planets. Life on Earth had just barely crawled out of the oceans. That is the timescale we are talking about. The cosmic web is a structure where distance and time merge into the same thing. To cross it is to travel through history. And here is the final piece that ties everything together. The cosmic web is not just a map of where galaxies are. It is a map of where everything is. Every atom in your body was once part of a gas cloud somewhere on the web. That gas cloud collapsed into a star. The star fused hydrogen into helium, helium into carbon, carbon into oxygen. The star died in a supernova. The explosion scattered the newly forged elements into space. They drifted along a filament. Eventually they collected into a new gas cloud. That cloud collapsed into our sun. The leftover material formed planets. One of those planets was Earth. And here you are, made of atoms that have been flowing through the cosmic web for billions of years, sitting on a rock orbiting a star in a galaxy, on a minor filament in a supercluster that is itself just one small thread in a web that spans the entire observable universe. The cosmic web is where you came from. It is the structure that organized the raw material of the universe into galaxies and stars and planets and eventually people. Without the web, without the filaments and voids and clusters, matter would be spread evenly across space. There would be no concentrations, no galaxies, no stars, no chemistry, no life. The web is not just a map. It is the reason anything exists at all. It is the scaffolding that cradles everything, and it is unimaginably vast. NASA's own description puts it plainly. The web forms as the gravitational attraction of the universe's matter draws larger and larger objects together. It is a structure billions of years in the making, a network built by gravity and time, and it contains everything. So when you think about the Milky Way, do not think of it as an isolated object floating in empty space. Think of it as a node on a thread, a single galaxy sitting on a filament that stretches across hundreds of millions of light years. That filament connects to other filaments. Those filaments meet at clusters. The clusters connect into superclusters, and the superclusters weave together into a web that fills the observable universe. The Milky Way is part of something much larger, and that larger thing is part of something larger still. The hierarchy extends until you reach the scale of the cosmos itself. We have mapped the structure. We have traced the filaments. We have measured the voids. We have counted the clusters. And the number of galaxies sitting on this web, the total count of every galaxy in the observable universe, is a number so large it defies comprehension. 2 trillion galaxies, each one containing billions or trillions of stars, each one a world unto itself, and all of them, every single one, sitting somewhere on the cosmic web, connected by filaments, separated by voids, held together by dark matter, organized by gravity, and expanding, slowly, inexorably, as the universe itself grows larger. That is the structure, that is the web, that is the framework that holds everything together, and it is only the beginning of understanding just how impossibly small we really are. We just traced the cosmic web across billions of light years, filaments stretching like highways between galaxy clusters, voids spanning hundreds of millions of light years with almost nothing inside them, superclusters woven together into a pattern so vast it fills the entire observable universe. A structure so large that the Milky Way, for all its 100,000 light years and 400 billion stars, becomes invisible. A single thread in a tapestry too big to see all at once. And now we need to talk about how many threads there are. Because the cosmic web is not empty. It is not sparse. It is not a few isolated galaxies scattered across infinite darkness. The universe is full, packed, crowded with galaxies in a way that defies every instinct the human brain has about what empty space should look like. When astronomers finally counted them, when they added up every galaxy they could see and extrapolated to every galaxy they could not, the number they arrived at was so large it forced a complete recalibration of how we think about our place in the cosmos. 2 trillion galaxies. That is the estimate. 2 trillion. Not 2,000, not 2 million, not 2 billion. 2 trillion separate galaxies scattered across the observable universe, each one a collection of billions or trillions of stars, each one containing gas and dust and planets and black holes and possibly life. Each one a world unto itself, and there are 2 trillion of them. The Milky Way is one, Andromeda is one, Triangulum is one. The other 1,999,999,999,997 galaxies are out there right now. Most of them so far away we will never see them in detail. Many of them so distant their light has not reached us yet and never will. 2 trillion galaxies. Let that number sit for a second, because it is not a number your brain can hold. It is too large. It exceeds the scale at which human intuition works. You can picture 100 galaxies, maybe 1,000 if you imagine them scattered across a dark field. But 2 trillion is beyond visualization. It is a number that only makes sense in comparison to other incomprehensibly large numbers, and even then it barely registers. Here is one way to think about it. There are roughly 400 billion stars in the Milky Way. Some estimates go higher, some go lower. 400 billion is a reasonable middle ground. If there are 2 trillion galaxies in the observable universe, and each galaxy contains on average a few 100 billion stars, then the total number of stars in the observable universe is somewhere in the range of 200 billion trillion. That is 2 followed by 23 zeros, 200 sextillion stars. The number of stars in the universe outnumbers the grains of sand on every beach and desert on Earth, not by a little, by a lot. Estimates for the total number of grains of sand on Earth usually come in around 7 quintillion. That is 7 followed by 18 zeros. The universe contains roughly 30,000 times more stars than Earth contains grains of sand. 30,000 Earths, every beach, every desert, every sandbox, every handful of dirt with sand in it. Multiply all of that by 30,000 and you are still not at the number of stars in the observable universe. Another way to think about it: if you tried to count the galaxies in the observable universe, one per second, without stopping, without sleeping, without pausing for food or water or rest, it would take you more than 63,000 years. You would have to start counting in the Stone Age and keep going through every empire, every war, every technological revolution, through the invention of writing and agriculture and cities and computers, and you would still be counting today. And you would not be finished for another 30,000 years. That is how many galaxies there are, 2 trillion. An almost meaningless number, made slightly less meaningless by comparing it to other absurd scales. The estimate did not come from a single observation. It came from decades of work, layer upon layer of surveys and images and extrapolations, each one refining the count, each one pushing the number higher. For most of the 20th century, astronomers thought there were maybe 100 billion galaxies in the observable universe. That was the textbook number, 100 billion. It was already an enormous number, already enough to make the Milky Way feel small, but it was based on incomplete data. The surveys that produced that estimate could only see the brightest galaxies, the big ones, the nearby ones, the galaxies that were easy to spot. Everything else was hidden in the noise, too faint, too distant, too small. Then, in 1995, astronomers did something that seemed pointless at the time. They pointed the Hubble Space Telescope at a tiny patch of apparently empty sky in the constellation Ursa Major and left it there for 10 days. 10 days of exposure time, 273 hours, staring at nothing. The patch of sky they chose was smaller than a grain of sand held at arm's length. A speck, a dot, a region so unremarkable that no one had bothered to study it before. They called it the Hubble Deep Field. The expectation was that they might find a few faint galaxies, maybe a few dozen, enough to get a sense of what was out there in the deep background. What they found instead was more than 3,000 galaxies. 3,000. In a patch of sky the size of a pinhead. Galaxies of every shape and size and color. Spirals, ellipticals, irregulars, some of them so distant that their light had been traveling for more than 12 billion years. Galaxies that existed when the universe was less than 1 billion years old. All of them packed into a region of sky so small you could cover it with a dime. The implications were immediate and uncomfortable. If a random patch of sky that small contained 3,000 galaxies, then the entire sky must be filled with them, billions of them, maybe hundreds of billions. The Hubble Deep Field was not showing us a unique region of space. It was showing us what space looks like everywhere, dense, crowded, full. Every direction you point a telescope, if you look deep enough, you find thousands of galaxies. The universe is not mostly empty, with a few galaxies scattered here and there. It is a sea of galaxies, stretching in every direction as far as light has had time to travel. Hubble did it again in 2003 and 2004 with the Hubble Ultra Deep Field. This time, they stared at an even smaller patch of sky for even longer. More than 11 days of total exposure time spread across 4 months. The image they produced is one of the most famous in astronomy. A deep black field dotted with thousands of faint smudges of light. Almost every single smudge in that image is a galaxy, not a star, a galaxy. Some of them are nearby, bright, detailed. You can see their spiral arms, their cores, their star-forming regions. Others are so faint they barely register. Tiny red dots sitting at the edge of detection. Galaxies so distant that the universe was less than 1 billion years old when their light began its journey toward Earth. The ultra-deep field contains about 10,000 galaxies. 10,000 galaxies in a patch of sky 1/10 the diameter of the full moon. If you covered the entire sky with patches like that, you would find tens of billions of galaxies. And that was just counting the ones Hubble could see. The problem was that Hubble had limits. It could see faint galaxies, it could see distant galaxies, but it could not see everything. The farther back you look, the more the light from galaxies gets redshifted into the infrared. Hubble's instruments were optimized for visible and near-infrared light. Anything farther out, anything more distant, anything redshifted beyond a certain point, Hubble missed. It was like trying to count fish in the ocean by looking at the surface. You could see some of them, the big ones, the ones near the top. But most of the ocean was below the visible layer, and you had no way to know how many fish were down there in the dark. In 2016, astronomer Christopher Consolis and his team at the University of Nottingham published a paper that tried to account for the missing galaxies. They took Hubble's data from the deep fields and other surveys, combined it with data from other telescopes, and used statistical models to estimate how many faint, small, distant galaxies were out there that Hubble could not detect. The math was straightforward. If you can see 10,000 galaxies in a patch of sky this size, and you know your telescope can only detect galaxies brighter than a certain limit, then you can estimate how many fainter galaxies are sitting below that limit. You model the distribution, you extrapolate, you correct for the stuff you missed. When Consolis's team did that calculation and scaled it up to the entire observable universe, the number they got was 2 trillion galaxies, a tenfold increase over the previous estimate. Suddenly the universe was not 100 billion galaxies, it was 2 trillion. That number shook the field. Not because it was impossible, not because it contradicted anything fundamental about cosmology, but because it forced a reckoning with scale. 2 trillion galaxies meant the Milky Way was even more insignificant than anyone had thought. It meant the local group was a footnote. It meant Laniakea, that vast supercluster containing 100,000 galaxies, represented only 0.005% of the galaxies in the observable universe. 0.005%, a rounding error, a speck. The estimate has been debated since it was published. Some astronomers think 2 trillion is too high. Some think it is too low. The James Webb Space Telescope, which came online in 2021, has started to refine the count. Webb can see deeper into the infrared than Hubble ever could. It can detect galaxies that are so faint and so distant that they were completely invisible to previous instruments. And every time Webb points at a patch of sky and stares, it finds more galaxies, faint red smudges sitting at the edge of the observable universe. Galaxies that existed less than 300 million years after the Big Bang. Galaxies that should not have had time to form yet according to some models, but are there anyway, glowing faintly in the deep infrared, waiting to be counted. Some recent estimates suggest the true number of galaxies in the observable universe could be higher than 2 trillion, maybe several trillion, maybe tens of trillions if you count the smallest dwarf galaxies that are barely more than large star clusters. The exact number depends on where you draw the line. What counts as a galaxy? Does a clump of 10 million stars orbiting a larger galaxy count? What about a clump of 1 million, 100,000? The definition gets fuzzy at the low end. But even if you only count galaxies with more than 1 billion stars, the number is still in the trillions. The universe is full. It is saturated with galaxies. Every direction you look, every patch of sky you sample, you find them. Thousands of them, millions of them, stretching back to the edge of time. Here is what that means. The Milky Way is not special. It is not unique. It is not even unusually large. There are bigger galaxies, there are smaller galaxies, there are brighter galaxies and dimmer galaxies, and galaxies of every shape and structure you can imagine. Spirals like the Milky Way and Andromeda, giant ellipticals like Messier 87 that look like glowing footballs, irregular galaxies that have no clear structure at all, just chaotic blobs of stars. Dwarf galaxies so small they contain only a few billion stars. Ultra-diffuse galaxies that are spread so thin they are almost invisible, even though they span tens of thousands of light years. Ring galaxies where a collision has created a circular wave of star formation. Lenticular galaxies that sit somewhere between spirals and ellipticals. Starburst galaxies where new stars are forming at a rate hundreds of times faster than normal. Active galaxies with supermassive black holes at their cores, spewing jets of radiation across millions of light years. Every variation, every configuration, every possible outcome of billions of years of gravitational collapse and cosmic evolution. And there are 2 trillion of them. The diversity is staggering. If you could somehow visit every galaxy in the observable universe, you would never see the same thing twice. Every galaxy has its own history, its own population of stars, its own chemistry, its own structure. Some galaxies are ancient, formed in the first few 100 million years after the Big Bang, their stars old and red and quiet. Some are young, still actively forming stars, their spiral arms glowing blue with newborn suns. Some are dead, their star formation shut down billions of years ago, their gas stripped away by collisions or by the hot plasma between galaxies in a cluster. Some are colliding right now, tangled together in slow-motion mergers that will take hundreds of millions of years to complete. Some are isolated, drifting alone through intergalactic space with no neighbors for millions of light years. Every galaxy is a story, and there are 2 trillion stories. The implication for life is immediate and overwhelming. If there are 2 trillion galaxies, and each galaxy contains on average a few 100 billion stars, and even a small fraction of those stars have planets, and even a tiny fraction of those planets are in the habitable zone where liquid water can exist, then the number of potentially habitable worlds in the universe is so large it becomes almost certain that life exists elsewhere. The math is simple. 2 trillion galaxies, a few 100 billion stars per galaxy. That is 200 billion trillion stars. Call it 10 to the 23rd power. If even 1 in a million of those stars has a planet in the habitable zone, that is still 10 to the 17th potentially habitable planets. 100 quadrillion, 100,000 trillion, planets where liquid water could exist, where chemistry could happen, where, given enough time, life might emerge. The odds that Earth is the only planet in the entire universe where life developed are so low they approach 0. Not impossible, just wildly improbable. That does not mean intelligent life is common. It does not mean we will ever make contact. The distances are too vast. Even if intelligent civilizations exist in every galaxy, The space between galaxies is so enormous that communication would take millions or billions of years. A signal sent from a planet in Andromeda would take 2.5 million years to reach Earth. By the time we received it, the civilization that sent it might be extinct. The universe could be full of life, full of intelligence, full of civilizations building telescopes and wondering if they are alone, and we would never know. The cosmic web connects galaxies gravitationally but not practically. The voids are too large. The expansion of the universe is too fast. Most galaxies are unreachable. We will never visit them. We will never communicate with anything inside them. We can only look. And when we look, what we see is 2 trillion islands, each one as isolated as ours, each one potentially containing billions of worlds, and none of them close enough to touch. Here is the hardest part to process. Most of those 2 trillion galaxies are invisible, not because they are too faint, though many are, but because their light has not reached us yet, or because their light will never reach us. The universe is expanding, and the farther away a galaxy is, the faster it is moving away from us. Beyond a certain distance, galaxies are receding faster than the speed of light. Not because they are moving through space faster than light, which is impossible, but because the space between us and them is expanding faster than light can cross it. The result is the same. Their light will never reach us. They are beyond the observable horizon, outside the bubble of space from which light has had time to reach Earth since the Big Bang. Those galaxies exist. They are real. They are out there right now. But we will never see them. They are invisible, permanently. And as the expansion accelerates, more and more galaxies will cross that horizon. The observable universe is shrinking. Distant galaxies are disappearing from view one by one as they are carried away by the expansion of space. In a few trillion years, most of the 2 trillion galaxies we can see today will be gone. The night sky will be darker, the cosmic web will look thinner, and eventually, the only galaxies left in the observable universe will be the ones in our local neighborhood, the ones gravitationally bound to us, the ones that are close enough that their mutual gravity can resist the expansion. That is maybe a few dozen galaxies. Everything else will be gone. Redshifted into invisibility, the universe will still be full. There will still be trillions of galaxies out there, but we will not be able to see them. We are living in a unique era. A brief window in cosmic history when the universe is old enough to have formed galaxies, but young enough that we can still see most of them. A few billion years from now, that window will start to close. The expansion will accelerate, the distant galaxies will fade. Future civilizations, if they exist, will look up at the sky and see almost nothing. A few nearby galaxies, a lot of darkness. They will not have the data we have. They will not be able to map the cosmic web, or count the galaxies, or measure the expansion. They will live in a universe that looks empty, and they will have no way to know it is not. We are lucky. We are living at the right time. The time when the universe is revealing itself. The time when we can still see the full picture. Or at least as much of it as light has had time to show us. So when you think about 2 trillion galaxies, think about what that number represents. It is not just a count. It is a statement about the universe. It is evidence that whatever process formed the Milky Way was not special. It was not unique. It happened 2 trillion times, and it is still happening, right now. Somewhere in the universe, gas is collapsing. Stars are forming. A new galaxy is being born. It has been happening for 13.8 billion years, and it will keep happening until the universe runs out of gas, until the last star dies, until the expansion of space pulls everything so far apart that nothing can ever collapse again. We are living in the age of galaxies. the age when the universe is full of light and structure and complexity. And 2 trillion galaxies are the proof. The Milky Way is one grain of sand on a beach that stretches farther than you can walk. One star in a sky so crowded with stars that you cannot see the darkness between them. One thread in a web so vast that light itself takes longer than the age of civilizations to cross it. The Milky Way is home. It is everything we have ever known. Every human who has ever lived was born inside it. Every star we can see with our naked eyes is part of it. Every constellation, every myth, every navigation system sailors used for thousands of years, all of it, the entire human experience, has taken place inside one galaxy, one of 2 trillion. And most of those other galaxies are larger, most are older, most contain more stars. The Milky Way is not the biggest. It is not the brightest. It is not the oldest, or the most massive, or the most interesting. It is average, unremarkable. One galaxy among trillions, indistinguishable from a distance, invisible from far enough away. And if that does not make you feel small, then you have not been paying attention. 2 trillion galaxies, an ocean of stars, a sea so vast that every drop contains billions of suns. And we are sitting on one planet, orbiting one star, in one galaxy, in one corner of one supercluster, on one thread of the cosmic web, staring out at the rest and trying to comprehend what it means. The scale is beyond us. It always has been, but we keep looking, we keep counting. We keep building better telescopes and mapping deeper into the darkness. And every time we do, the universe gets bigger. The count goes up, the number of galaxies increases, and the Milky Way, for all its beauty and complexity, shrinks a little more. But we are not done yet, because 2 trillion galaxies is just the count, it is just the number. To understand what it really means, to grasp the full scale of the cosmos, we need to talk about the edges, the boundaries, the limits of how far we can see. We need to talk about the observable universe itself, the bubble of space from which light has had time to reach us. And we need to ask the question that has haunted cosmology since the beginning. How big is it really? How far does it go? And is there anything beyond the edge? We just counted 2 trillion galaxies, 2 trillion separate islands of stars scattered across the cosmic web, each one containing billions or trillions of suns, each one sitting somewhere on a filament or in a cluster or drifting alone through a void. The number is so large it stops meaning anything. Your brain cannot hold it, mine cannot either. But we counted them anyway. We mapped them, we catalogued them. We measured their distances and their brightnesses and their redshifts. And when we finished, when we added up everything we could see and everything we could infer, the total came to 2 trillion galaxies in the observable universe. That last word matters, observable. Because the universe is not 2 trillion galaxies. The universe might be infinite. It might contain an infinite number of galaxies stretching forever in every direction. Or it might be finite but unimaginably vast, containing trillions upon trillions of galaxies that we will never see. We do not know, we cannot know, because there is a limit to how far we can see, a boundary, an edge, not an edge to the universe itself, an edge to what we can observe. A horizon beyond which light has not had time to reach us. And that horizon, that bubble of space from which light has had time to travel since the beginning of everything, is what we call the observable universe. The observable universe is roughly 93 billion light-years across. Let me say that again because the number does not make sense at first. 93 billion light-years. The universe is 13.8 billion years old. Light has been traveling toward us for 13.8 billion years. You would think, reasonably, that the farthest we could see would be 13.8 billion light-years away, a light-year for every year the universe has existed. That would make the diameter of the observable universe about 27.6 billion light-years. Double the age because light is coming from both directions. Simple, logical, wrong. The actual diameter is 93 billion light-years, more than 3 times what you would expect. And the reason for that discrepancy is the same reason everything in cosmology gets complicated. The universe is expanding, space itself is stretching, and while light has been traveling toward us for 13.8 billion years, the space it has been traveling through has been expanding the entire time. The result is that objects which emitted light 13.8 billion years ago are not 13.8 billion light-years away anymore. They are much farther, roughly 46 billion light-years away in every direction. Double that and you get 93 billion. That is the size of the observable universe. Not the size of the universe, just the size of the part we can see. Here is how it works. Imagine you are standing on a long moving walkway at an airport, the kind that carries you forward while you walk. Now imagine the walkway is stretching as you walk on it. Every step you take, the walkway gets a little longer. You are moving forward, but the destination is moving away from you at the same time. If you walk fast enough, you will still reach the end eventually, but it will take longer than you expect. And when you finally arrive, the walkway will be much longer than it was when you started. That is what light does in an expanding universe. It moves toward us at the speed of light, but the space it is crossing is stretching. By the time the light reaches us, the object that emitted it is much farther away than it was when the light started its journey. That stretching is measurable. We call it redshift. As space expands, the wavelength of light traveling through it gets stretched too. Blue light becomes red light. Red light becomes infrared. The farther away an object is, the more its light has been stretched. And by measuring how much the light has been stretched, we can calculate how far away the object is and how long the light has been traveling. The most distant galaxies we have ever observed have redshifts so extreme that their light has been stretched by a factor of 10 or more. Ultraviolet light emitted when the universe was less than 1 billion years old arrives at Earth as deep infrared. The James Webb Space Telescope was built specifically to detect that light, and it has found galaxies sitting at the very edge of the observable universe. Galaxies whose light has been traveling toward us for more than 13 billion years. Galaxies that are now sitting roughly 46 billion light-years away because the space between us and them has been expanding the entire time. So the observable universe is a sphere centered on Earth. It extends roughly 46 billion light-years in every direction. Everything inside that sphere is observable in principle. Everything outside it is not. The boundary is not a wall. It is not a surface. It is just a distance. The distance light has had time to travel since the Big Bang, and that distance is growing. Every second, light from slightly more distant regions reaches us for the first time. The observable universe is expanding at the speed of light, not because the universe itself is expanding that fast, but because light is always traveling, always covering new ground, always bringing us information from farther and farther away. 1 billion years from now, the observable universe will be larger. The boundary will have moved outward. We will be able to see galaxies that are currently beyond the horizon, and galaxies that are currently visible will be farther away. But here is the uncomfortable part. That expansion is accelerating. The universe is not just getting bigger, it is getting bigger faster, and there is a point, a distance beyond which galaxies are receding from us, faster than light can travel. Not faster than light through space, which is impossible. faster than light through expanding space, which is very much possible. If a galaxy is far enough away, the space between us and it is expanding so quickly that light leaving that galaxy right now will never reach us. It will travel toward us at the speed of light, covering billions of light years over billions of years, but the space in front of it will be stretching faster than it can cross. The light will make progress. It will get closer, but it will never arrive. The galaxy is beyond the cosmic horizon, outside the observable universe, permanently. That means there are galaxies out there right now whose light we will never see. Not because they are too faint, not because they are hidden behind something, but because the expansion of space has carried them beyond the point where communication is possible. They exist. They are real. They are filled with stars and planets and possibly life, but they are unreachable, invisible, cut off from us by the geometry of space-time itself. And as the expansion accelerates, more and more galaxies will cross that line. The observable universe is shrinking in a sense, not in size, but in content. Distant galaxies are disappearing from view one by one as they are carried over the horizon. In a few trillion years, the only galaxies left in the observable universe will be the ones in our local neighborhood, the ones gravitationally bound to us. Everything else will be gone, but we are not there yet. Right now, we can still see most of the universe. The observable bubble is large, 93 billion light-years across, and almost everything inside it is visible if you have a powerful enough telescope and enough time to stare. Almost everything. There is one region we cannot see, one moment in time that is hidden from us, and it sits at the very edge of the observable universe like a wall we can never cross. The cosmic microwave background, the CMB, it is the oldest light we can see, the farthest thing we can directly observe, and it is not a galaxy or a star or a quasar. It is the leftover glow from the moment the universe became transparent. About 380,000 years after the Big Bang, the universe cooled enough for hydrogen atoms to form. Before that, the universe was a hot, dense plasma, free electrons and protons bouncing around, scattering photons in every direction. Light could not travel in straight lines because it was constantly being absorbed and re-emitted. The universe was opaque, a glowing fog with no clear sight lines. Then it cooled just enough for electrons and protons to combine into neutral hydrogen. Once that happened, the photons were free. They stopped scattering. They started traveling in straight lines. The universe became transparent. And the light from that moment has been traveling through space ever since. That light is the cosmic microwave background. It is everywhere. Every direction you point a telescope, if you tune it to the right wavelength, you see it, a faint glow filling the entire sky. The light was originally emitted as visible light and ultraviolet, hot and bright, but it has been traveling for 13.8 billion years through expanding space. The wavelength has been stretched by a factor of about 1,000. What was once visible light is now microwave radiation. Cold, faint, just a few degrees above absolute zero. But it is there, and it is the same in every direction. The entire sky glows with this ancient light, a perfect sphere surrounding us at a distance of about 46 billion light-years. The edge of everything we can see. The CMB is not the edge of the universe. It is the edge of what we can observe with light. Before the CMB formed, the universe was opaque. Light could not travel freely. Any photons emitted before that moment were scattered and absorbed so many times that they carry no useful information. We cannot see through the CMB to earlier times. Not with light, not with any form of electromagnetic radiation. The CMB is a wall, a curtain. The earliest snapshot we have of the universe. Everything before it is hidden. Astronomers call the time before the CMB the Dark Ages, not because it was dark, it was actually incredibly bright, but because it is dark to us. We cannot see it. It is beyond the reach of telescopes. There are other ways to probe earlier times. Gravitational waves, ripples in space-time itself, can travel through the opaque early universe without being scattered. If we ever build detectors sensitive enough to pick up gravitational waves from the Big Bang, we might be able to see farther back. Neutrinos, ghostly particles that barely interact with matter, could also carry information from earlier times. But for now, the CMB is the limit. The farthest we can see, the oldest light we can detect, and it tells us an enormous amount. The CMB is not perfectly uniform. If you map it across the entire sky, you see tiny fluctuations in temperature, regions that are slightly hotter than average, regions that are slightly cooler. The differences are tiny, less than 1 part in 100,000, but they are there. And those tiny fluctuations are the seeds of everything. The denser regions in the early universe, the places where matter was slightly more concentrated, show up as warmer spots in the CMB. The less dense regions show up as cooler spots. Over billions of years, those tiny differences grew. Gravity pulled matter toward the denser regions. The dense regions got denser. The less dense regions got emptier. Eventually, the dense regions collapsed into galaxies and clusters and filaments. The less dense regions expanded into voids. The cosmic web we see today is the result of those tiny fluctuations in the CMB growing and amplifying over 13.8 billion years. The CMB is not just a snapshot of the early universe. It is a map of the initial conditions, a blueprint for everything that came after. NASA's Wilkinson Microwave Anisotropy Probe spent 9 years mapping the CMB in exquisite detail. The European Space Agency's Planck satellite did the same with even higher precision. The maps they produced are some of the most important images in all of science. They show the universe as it was 380,000 years after the Big Bang. A smooth, hot, nearly uniform glow with tiny ripples that would one day become galaxies and stars and planets and people. Every atom in your body was part of that glow once. Every element heavier than hydrogen and helium was forged in stars that formed because of those ripples. The CMB is not just the edge of the observable universe. It is the origin story, the earliest chapter, the moment when the lights turned on and the universe became something we could, in principle, observe. Here is the scale you need to understand. The CMB surrounds us at a distance of about 46 billion light-years. That light has been traveling toward us for 13.8 billion years. The galaxies we see in the deepest images from the James Webb Space Telescope are sitting maybe 12 or 13 billion light-years away in look-back time. Their light has been traveling for 12 or 13 billion years, but the CMB is older. Its light has been traveling for the entire age of the universe. It is the farthest thing we can see, the ultimate horizon, and beyond it there is nothing we can observe. Not because there is nothing there, but because the light from anything farther away has not had time to reach us yet. Or because the universe was opaque before that moment and light could not travel freely. That phrase matters. Look back time. When you look at a distant galaxy, you are not seeing it as it is now, you are seeing it as it was when the light left. If you look at a galaxy 10 billion light-years away, you are seeing it as it existed 10 billion years ago. That galaxy still exists today, probably, but it is not where you see it anymore. It has moved, it has evolved. Stars have formed and died. The galaxy might have merged with another galaxy. It might look completely different now, but you cannot see it as it is now. You can only see it as it was. The farther away you look, the farther back in time you see. Telescopes are time machines, not in the science fiction sense, but in the literal sense. They let us look into the past. The most distant galaxies ever observed are seen as they were less than 500 million years after the Big Bang. The James Webb Space Telescope has found galaxies at redshifts higher than 14. That corresponds to a look-back time of more than 13 billion years. These galaxies are sitting at the very edge of the observable universe, just barely inside the horizon, their light stretched into the deep infrared by the expansion of space. They are young, primitive, filled with the first generation of stars, and they are enormous, far more massive than galaxies that age should be according to standard models of galaxy formation. They should not exist yet, but they do, and we can see them, barely, faintly, but they are there. When we look at the CMB, we are looking back 13.8 billion years, almost the entire age of the universe. We are seeing light that was emitted when the universe was less than 400,000 years old. A baby universe, hot, dense, simple, no stars yet, no galaxies, no planets, just hydrogen and helium and a faint glow of radiation cooling as space expanded. That is the edge, the farthest we can see, the oldest light. And it is sitting 46 billion light-years away in every direction because the space between us and it has been expanding the entire time. So what lies beyond the CMB? What is outside the observable universe? The honest answer is, we do not know. We cannot know. By definition, anything beyond the observable universe is unobservable. Its light has not reached us. Its information has not crossed the horizon. It might as well not exist as far as our ability to measure it is concerned, but that does not mean it is not there. The universe almost certainly extends beyond what we can see. The observable universe is just a bubble, a sphere of space from which light has had time to reach us. The actual universe, the full universe, could be vastly larger. It could be infinite. It could contain trillions upon trillions of galaxies that we will never see. Or it could be finite, but so large that the observable universe is just a tiny patch, a single pixel in a much larger image. There are hints that the universe is much larger than what we can observe. The CMB is remarkably uniform. The temperature is the same in every direction to within 1 part in 100,000. That uniformity is a problem. Different regions of the CMB are so far apart that light has not had time to travel between them since the Big Bang. They should not be in thermal equilibrium. They should not have the same temperature, but they do. The standard explanation is called inflation. A brief period in the very early universe, less than a second after the Big Bang, when space expanded exponentially fast, faster than light, much faster. In a tiny fraction of a second, the universe grew from smaller than an atom to larger than a galaxy. That rapid expansion smoothed out the temperature. Regions that were once close together, in contact, able to exchange heat, were suddenly separated by vast distances, and when inflation ended, the universe continued expanding at a more sedate pace. The observable universe we see today is just a small patch of a much larger inflated space. The full universe could be millions or billions of times larger than what we can see, or it could be infinite. Inflation does not tell us the size. It just tells us that what we can see is probably not the whole story. If the universe is infinite, then there are an infinite number of galaxies, an infinite number of stars, an infinite number of planets, an infinite number of worlds where life might exist. Somewhere out there, beyond the horizon, there could be an exact copy of Earth, an exact copy of you. Reading this exact script, the probability is unimaginably small, But in an infinite universe, anything that is possible, no matter how unlikely, happens an infinite number of times. That is the math. That is what infinity means. It is deeply uncomfortable, and it might be true. We do not know. What we do know is that the observable universe is large enough, 93 billion light-years across, 2 trillion galaxies, 100 billion trillion stars, a cosmic web of filaments and voids and clusters stretching across the entire visible cosmos. The Milky Way is one galaxy among trillions. The local group is one cluster among millions. Laniakea is one supercluster among thousands. And all of it, every galaxy we have ever seen or ever will see, sits inside a sphere 46 billion light-years in radius, centered on a small blue planet orbiting an average star in an unremarkable part of an ordinary galaxy. That sphere is not special. It is not the center of the universe. It is just the region from which light has had time to reach us. An alien civilization in a galaxy 10 billion light-years away would see their own observable universe, a different sphere, centered on them, overlapping with ours, but extending in different directions, and their view would show galaxies we will never see. Just as our view shows galaxies they will never see. Every observer has their own horizon, their own observable universe, and none of them are special. The edge of the observable universe is not a place you can travel to. It is not a wall you can touch. It is a distance, a limit imposed by the speed of light and the age of the universe, and it is always moving. Every second, light from farther away reaches us for the first time. The boundary shifts outward at the speed of light. We are always at the center of an expanding bubble, not because we are special, but because we are observers. The bubble is defined by what we can see, and what we can see is limited by how far light has had time to travel. But here is the final uncomfortable truth. That bubble is temporary. The observable universe is not going to keep growing forever. Right now, the expansion of space is accelerating. Something we call dark energy is pushing galaxies apart faster and faster. And because of that acceleration, there is a distance beyond which galaxies are receding faster than light, the cosmic event horizon. Galaxies beyond that horizon are unreachable. Their light will never reach us, and as the expansion accelerates, that horizon is getting closer, not in distance, but in content. More and more galaxies are crossing the horizon every moment, disappearing from view, redshifted into invisibility. In a few trillion years, the observable universe will contain only the galaxies in our local gravitationally bound group, a few dozen at most. Everything else will be gone. The sky will be dark. The cosmic web will be invisible. And future astronomers, if they exist, will look up and see almost nothing. They will have no way to know that the universe was once filled with trillions of galaxies, no way to measure the expansion, no way to discover the Big Bang. They will live in a universe that looks empty and static, and they will be wrong, but they will have no data to tell them otherwise. We are living in a brief window, a few billion years, when the universe is old enough to have formed galaxies, but young enough that we can still see most of them. The cosmic web is visible. The CMB is detectable. The expansion is measurable. We can map the structure of the universe and trace its history back to the first few 100,000 years. That window is closing, slowly, but inevitably. The universe is revealing itself to us right now. And in a few trillion years, it will stop. The data will be gone. The evidence will be hidden. The cosmos will go dark. But we are here now. We can see it. We can measure it. We can map the observable universe in all its vastness and complexity. 93 billion light-years across. 2 trillion galaxies. a cosmic web stretching to the edge of visibility, and a boundary, a horizon, a curtain of ancient light marking the farthest we can ever see. The CMB, the edge of forever, the limit of observation, and beyond it, hidden from view, possibly infinite, possibly just unimaginably vast, lies the rest of the universe, a place we will never see, a place that might contain more galaxies than we can count, a place that is expanding away from us faster than light can follow. The observable universe is enormous, and it is nothing, a bubble in an ocean, a patch of visibility in a cosmos that might stretch forever. We can see 93 billion light-years, and that might be the tiniest fraction of what actually exists. The Milky Way is not just small compared to the observable universe, it is small compared to what might lie beyond it. And that beyond is driven by something we still do not fully understand, a force that is tearing the cosmos apart, a force that has been accelerating the expansion for the last few billion years, a force that will eventually determine the fate of everything. We call it dark energy, and it is winning. We just traced the observable universe to its edges, 93 billion light-years across, 2 trillion galaxies, a cosmic web stretching to the limits of what light has had time to show us. The cosmic microwave background sitting at the horizon like a curtain we can never pull back. The farthest thing we can see, the oldest light, the edge of forever. And we talked about how that edge is moving, how every second, light from slightly farther away reaches us for the first time, how the observable universe is growing as photons that have been traveling for billions of years finally complete their journey and arrive at our telescopes. That story is comforting. It suggests the universe is opening up to us, revealing more of itself. Year by year, century by century, the bubble of what we can observe expands, and we get to see deeper into the cosmos. More galaxies, more structure, more history. The narrative feels like progress, like discovery, like the universe wants to be seen. Except that is not the whole story. The observable universe is growing in one sense, but in another, more important sense, it is shrinking. Not in size, in content. Galaxies are disappearing. Not because they are dying, not because they are being destroyed, but because they are being carried away from us so fast that their light will never reach us again. The expansion of the universe is not slowing down the way gravity should make it slow down. It is speeding up, accelerating, and that acceleration is driven by something we do not understand, something we cannot see, something that makes up 70% of the universe and has been pulling the cosmos apart for the last few billion years. We call it dark energy. And it is the reason the universe will eventually go dark. The story starts with a supernova. Actually, it starts with dozens of them. Type Ia supernovae to be specific. These are exploding white dwarf stars that detonate when they accumulate too much mass from a companion star and cross a critical threshold. The physics of that threshold is well understood. It happens at almost exactly the same mass every time. And because the explosion always happens at the same mass, the brightness of the explosion is always roughly the same. That makes Type Ia supernovae incredibly useful. They are what astronomers call standard candles, objects whose true brightness is known. If you know how bright something truly is, and you measure how bright it looks from Earth, you can calculate how far away it is. The math is simple. Brightness falls off with the square of distance. Measure the apparent brightness, compare it to the true brightness, and you have a distance. In the 1990s, 2 independent teams of astronomers decided to use Type Ia supernovae to measure the expansion of the universe. The goal was straightforward: find supernovae in distant galaxies, measure their brightness, calculate their distances. Compare those distances to how fast the galaxies are receding, and from that, figure out whether the expansion of the universe is slowing down. Because it should be slowing down. Gravity pulls everything together. The universe is full of matter. Matter has mass. Mass creates gravity. Gravity should be putting the brakes on the expansion, not stopping it entirely, probably, but at least slowing it down over time. That was the expectation. The only question was how much the expansion had slowed. Was it slowing fast enough that the universe would eventually stop expanding and collapse back on itself in a big crunch? Or was it slowing gently, coasting toward a future where the expansion continues forever but gets slower and slower? The two teams were rivals. Friendly rivals, mostly, but rivals nonetheless. One team was the Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other was the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University, with Adam Rees at Johns Hopkins playing a key role in the analysis. Both teams spent years developing the techniques to find and measure distant supernovae. Both teams competed to be the first to publish results. Both teams expected to measure a decelerating universe, a universe where gravity was winning, a universe where the expansion was slowing down. In 1998, both teams announced their results. The universe was not slowing down. It was speeding up. The supernovae were dimmer than they should have been, not by a lot, but enough that it was unmistakable once you accounted for the uncertainties. If the supernovae were dimmer than expected, that meant they were farther away than expected. And if they were farther away than expected, that meant the universe had expanded more than it should have in the time since the light left those galaxies. The expansion had accelerated. Somewhere in the last few billion years, something had started pushing the universe apart faster and faster. Not gravity. Gravity pulls. This was something else, something that pushes, something repulsive. NASA describes the finding as a total shock to astronomers. That is not an exaggeration. The discovery overturned the basic expectation that had guided cosmology for decades. Everyone knew the universe was expanding. Edwin Hubble had proven that in the 1920s. Everyone expected gravity to slow that expansion. The only debate was whether it would slow enough to reverse or just coast forever. Nobody expected it to accelerate. Nobody had a theory that predicted it. And yet there it was in the data. Supernova that were too dim, galaxies that were too far. An expansion that was speeding up when it should have been slowing down. The two teams initially did not believe their own results. They checked everything. They recalibrated. They looked for systematic errors. They wondered if dust was dimming the supernovae, making them look farther away than they really were. But the dust explanation did not work. Dust reddens light. It makes blue light look redder. The supernovae were not redder than expected. They were just dimmer. The data held. The conclusion was unavoidable. The expansion of the universe was accelerating, and if it was accelerating, something had to be pushing it. Something with enough energy to overcome the gravitational pull of all the matter in the universe. Something that filled all of space. Something invisible. Something no one had ever detected directly. They called it dark energy. Not because anyone knew what it was, but because they needed a name. Dark energy is a placeholder, a label for an effect whose cause is still unknown. It is not a substance. It is not a particle. It is not a field in the way electromagnetism or gravity is a field. Or if it is, we have not figured out the rules yet. Dark energy is simply the name for whatever is causing the expansion to accelerate. And by measuring how much the expansion is accelerating, astronomers have been able to calculate how much dark energy there is. The answer is roughly 70% of the total energy in the universe. Not 70% of the matter, 70% of everything. Matter, both visible and dark, makes up the other 30%. Dark energy is the dominant component of the cosmos. It outweighs everything else, and we have no idea what it is. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for the discovery. The prize citation was clear. They had found evidence that the expansion of the universe is accelerating. They had overturned the prevailing model. They had forced cosmologists to confront a universe that was stranger and more mysterious than anyone had expected. And they had opened a question that remains unanswered to this day. What is dark energy? There are a few ideas. The simplest is that dark energy is a property of space itself, a cosmological constant. Einstein introduced this concept in 1917 when he was trying to build a model of the universe that was static, neither expanding nor contracting. He added a term to his equations of general relativity, a constant that represented a kind of repulsive force inherent in empty space. The idea was that this repulsive force would balance gravity and keep the universe stable. Then Hubble discovered the universe was expanding, and Einstein reportedly called the cosmological constant his biggest blunder. He removed it from his equations, but it turns out he might have been right after all. If dark energy is a cosmological constant, then every cubic meter of space contains a tiny amount of energy. Not much, just enough to create a very gentle outward push. But because space is so vast, that tiny push adds up. And as the universe expands, there is more space, more cubic meters, more dark energy. The push gets stronger, the expansion accelerates. The cosmological constant does not change. It is the same everywhere, the same at all times. But the amount of space increases, so the total amount of dark energy increases, and the repulsion grows. That explanation has problems. For one thing, when physicists try to calculate what the energy density of empty space should be based on quantum field theory, they get a number that is 10 to the power of 120 times larger than what we observe. That is not a small error. That is the worst prediction in the history of physics, off by more than 100 orders of magnitude. So either quantum field theory is catastrophically wrong about the vacuum, or dark energy is not a cosmological constant, or there is some unknown mechanism that cancels out almost all of the vacuum energy, leaving just a tiny residual amount. Nobody knows which. It is an open problem. A crack in the foundation of modern physics. Another possibility is that dark energy is not constant. Maybe it changes over time. Maybe it is a field that evolves as the universe expands. Astronomers call this idea quintessence, named after the fifth element in ancient Greek philosophy. If dark energy is quintessence, then its strength could vary. It could have been weaker in the early universe, stronger now. And it could get even stronger in the future, or weaker, or it could oscillate. The behavior would depend on the properties of the field, and we do not know what those properties are because we have never detected the field directly. Quintessence is a hypothesis, a model that fits the data but has no independent confirmation. A third possibility, more radical, is that dark energy does not exist at all. Maybe general relativity is wrong at the largest scales. Maybe gravity behaves differently across billions of light years than it does in the solar system. Maybe the equations that work so well for planets and stars and black holes break down when you apply them to the entire universe. There are modified gravity theories that try to explain cosmic acceleration without invoking dark energy. None of them work as well as the standard model. None of them fit all the data cleanly, but they are out there. Alternatives. attempts to explain the acceleration without adding a mysterious new component to the universe. For now, the simplest explanation that fits the data is that dark energy is real. It makes up about 70% of the universe. It has been accelerating the expansion for the last few billion years, and it is not going away. NASA describes it as a mysterious repulsive force that makes the universe expand at an increasing rate. That is as close to a definition as we have. A force, repulsive, mysterious, accelerating the expansion, and its effects are profound. Here is what dark energy does. It pushes galaxies apart, not by exerting a direct force on them, but by expanding the space between them. Think of it like a loaf of raisin bread rising in an oven. The dough expands. The raisins do not move through the dough. They just get carried along as the dough rises. The farther apart two raisins are, the faster they move away from each other because there is more dough between them expanding. Galaxies are the raisins, space is the dough, and dark energy is the yeast making the dough rise faster and faster. The farther apart two galaxies are, the more space there is between them. The more space there is, the faster it is expanding. The faster it expands, the faster the galaxies recede from each other. Close galaxies, galaxies that are gravitationally bound like the Milky Way and Andromeda, are not affected. Their mutual gravity is strong enough to resist the expansion. They are like raisins stuck together in the dough. The dough around them rises, but they stay together. The local group will not be torn apart by dark energy. Neither will the Virgo cluster. Gravitationally bound structures, clusters and groups are dense enough that gravity wins, but the space between clusters is expanding. The clusters themselves are drifting apart. The cosmic web is stretching. The filaments are getting longer. The voids are growing. And as the expansion accelerates, the recession speeds increase. Right now, galaxies in the Virgo cluster are receding from us at about 1,000 kilometers per second. Galaxies farther out are receding faster. Galaxies several billion light-years away are receding at a significant fraction of the speed of light. And beyond a certain distance, galaxies are receding faster than the speed of light, not through space, through expanding space. That distinction matters. Nothing can move through space faster than light. That is a rule of relativity, and it holds. But space itself can expand as fast as it wants. There is no speed limit on the expansion of space. And when space expands fast enough, objects embedded in it can be carried away from each other faster than light can travel between them. That creates a boundary, a horizon. The cosmic event horizon. If a galaxy is far enough away that the space between us and it is expanding faster than the speed of light, then light leaving that galaxy right now will never reach us. Not in 1 billion years, not in 1 trillion, never. The light will travel toward us. It will cover billions of light years, but the space in front of it will be expanding faster than it can cross. The photon will make progress. It will get closer. But the finish line will recede faster than the photon can run. The light will never arrive. The galaxy is beyond the horizon, unreachable, lost. The current estimate for the distance to the cosmic event horizon, assuming dark energy behaves like a cosmological constant, is about 16 billion light-years. That is the distance at which the recession speed equals the speed of light. Galaxies closer than 16 billion light-years are receding slower than light. Their light can still reach us eventually. Galaxies farther than 16 billion light-years are receding faster than light. Any light they emit from this moment forward will never reach us. They are over the horizon, gone. Here is the deeply uncomfortable part. Galaxies we can see today are crossing that horizon right now. Every moment, galaxies that are currently visible are being carried far enough away that any new light they emit will never reach us. We can still see them because we are looking at old light. Light that was emitted billions of years ago when those galaxies were closer. But the galaxies themselves have moved. They are farther away now than they were when the light left, and if they are far enough, they have crossed the horizon. We are seeing their past, but we will never see their future. The light that left those galaxies a billion years ago is still traveling toward us and will arrive eventually. But the light leaving them today is already lost. It will never complete the journey. The distance is too great. The expansion is too fast. Over time, more and more galaxies will cross the horizon. The observable universe, in terms of content, is shrinking, not in radius. The observable universe is still growing. Light from farther and farther away is still reaching us for the first time. But the galaxies themselves are moving away faster than new ones are becoming visible. The net effect is that the number of galaxies we can observe is decreasing, slowly, over billions of years, but inexorably. Distant galaxies are fading, red-shifting into invisibility. Their light stretched by the expansion of space until the wavelength is so long that no detector we build will ever pick it up. They are disappearing, not because they are dying, because they are leaving. In a few trillion years, the only galaxies left in the observable universe will be the ones in our local neighborhood, the local group, maybe a few nearby groups that are gravitationally bound to us. Everything else will be gone. The cosmic web will be invisible. The distant clusters and superclusters will have receded beyond the horizon. The sky will be dark, empty. A few dozen galaxies scattered across a vast black expanse. Future astronomers, if they exist, will have no evidence that the universe was once full of galaxies, no way to measure the expansion, no way to discover dark energy, no way to see the cosmic microwave background because it too will have red-shifted beyond detection. They will look up at the sky and conclude they live in a small, isolated, static universe. And they will be wrong, but they will have no data to tell them otherwise. We are living in a unique time, a window. The universe is old enough that galaxies have formed and matured, but young enough that most of them are still visible. The cosmic web is lit up, the expansion is measurable, the CMB is detectable. Dark energy has started to dominate, but it has not yet erased the evidence of the Big Bang. We can see the history of the universe written across the sky, but that history is being erased, slowly, page by page, galaxy by galaxy. The evidence is disappearing, the cosmos is closing itself off, and there is nothing we can do to stop it. Dark energy is not malicious. It is not trying to hide the truth. It is just a property of space, a gentle outward push that grows stronger as the universe grows larger. But the effect is the same: isolation, darkness, a future where the universe looks empty because everything has been carried so far away that light can no longer bridge the gap. The universe will still be full. There will still be trillions of galaxies out there, but they will be invisible, unreachable, beyond the horizon, cut off from us and from each other by the geometry of expanding space-time. NASA describes dark energy as the mysterious something causing the expansion to accelerate. That word, mysterious, carries weight. We do not know what dark energy is. We do not know why it exists. We do not know if it is constant or changing. We do not know if it will stay the same strength forever, or if it will get stronger or weaker over time. We do not even know for sure if it is a real thing or just a sign that our equations are wrong. What we know is the effect, the acceleration, the dimming of distant supernovae, the stretching of space, the galaxies slipping over the horizon one by one as the universe expands faster and faster. The discovery of dark energy was a shock because it violated expectations. Gravity should slow things down. The universe should be decelerating. Instead, it is accelerating. And the implications are vast, not just for cosmology, for the future of everything. If dark energy continues to dominate, if the acceleration continues, then the ultimate fate of the universe is cold and dark and empty. Galaxies will drift apart until they are alone. Stars will burn out, black holes will evaporate, and the universe will expand forever into a state of maximum entropy where nothing can ever happen again. Astronomers call it the Big Freeze or heat death, a universe that grows colder and darker and more diffuse until it reaches a final state where no energy can be extracted from anything. No work can be done, no life can exist, just darkness and silence stretching into eternity. That is trillions of years away, maybe tens of trillions, maybe more. The sun will die long before that. The Milky Way and Andromeda will merge and settle into a quiet elliptical galaxy. Most of the stars in that galaxy will burn out. The last stars, small red dwarfs, will flicker for trillions of years before finally going dark. And through all of that, dark energy will keep pushing, keep accelerating, keep expanding the universe, until the only thing left is cold, empty space stretching forever in all directions. That is the future dark energy has written. Not dramatic, not sudden, just slow, inevitable, lonely. But we are not there yet. We are here, now, in the brief window when the universe is revealing itself, when the evidence is still visible, when we can still see the galaxies and measure their distances and trace the history of the cosmos back to the first fraction of a second after the Big Bang. Dark energy is winning. It will eventually erase everything, but right now we can still see what it is erasing. We can map the cosmic web. We can count the galaxies. We can measure the acceleration. We can stare at the night sky and know that what we are seeing is temporary. A snapshot of a universe in transition. A universe moving from a bright connected web of galaxies to a dark, isolated future where nothing is visible beyond our local neighborhood. The observable universe is 93 billion light-years across, but the reachable universe, the part we could ever hope to communicate with or travel to even in principle, is much smaller, and it is shrinking. Every second, the boundary moves inward, not in distance, in content. Galaxies we can see today are crossing the cosmic event horizon. Their future light will never reach us. And as dark energy continues to accelerate the expansion, that horizon will keep moving closer in terms of which galaxies are still accessible. Eventually, the only galaxies left within reach will be the ones gravitationally bound to us, a few dozen, maybe a few hundred if we are generous with the definition. Everything else will be over the horizon, gone, invisible, lost to the expansion. That is the invisible hand. Dark energy, mysterious, repulsive, accelerating the expansion of the universe, pushing galaxies apart, stretching space, carrying distant galaxies over the horizon one by one until the universe goes dark. It is not malicious, it is not conscious, it is just physics. A property of space that we do not understand, but whose effects are undeniable. And it is the reason the Milky Way, small as it is, might one day be one of the only galaxies we can see. The reason the cosmic web will eventually fade. The reason the universe will end not with a bang, but with silence. We discovered dark energy by accident, by measuring supernovae and finding they were dimmer than expected. By doing careful science and trusting the data, even when the data contradicted everything we thought we knew. The 1998 discovery was a turning point, a moment when the universe revealed a secret it had been keeping for billions of years. The expansion was not slowing down, it was speeding up, and the thing causing it, whatever it was, made up most of the universe, more than matter, more than dark matter, more than everything we could see or touch or measure directly. An invisible force shaping the fate of the cosmos. And here is the final piece, the part that connects to what comes next. The observable universe is not the universe, it is just the part we can see. The part from which light has had time to reach us. Beyond that boundary, beyond the cosmic microwave background, beyond the horizon, the universe continues. It might be infinite, it might be vastly larger than what we observe, and dark energy does not stop at the edge of the observable universe. It is everywhere, accelerating the expansion everywhere, pushing galaxies apart everywhere, not just the ones we can see, all of them. The galaxies beyond the horizon are receding too, faster than light, carried away by the same dark energy that is slowly erasing the galaxies we can still observe. The universe is not just larger than we can see, it is growing faster than we can keep up with, and the part we can see is a shrinking fraction of the whole. So the observable universe is enormous. 93 billion light-years across, 2 trillion galaxies, but it is temporary, a bubble in a much larger cosmos. A bubble that is filling with darkness as the galaxies inside it drift over the horizon one by one. Dark energy is the reason, the invisible hand, the force we cannot see but whose effects dominate everything, and it is still out there, still pushing, still accelerating, still writing the future of the cosmos in a language we barely understand. The question is no longer how big the observable universe is. We have measured that. The question is how big the actual universe is, the full universe, the part we cannot see, the part beyond the horizon, the part that might stretch forever in every direction or might curve back on itself in ways we cannot yet imagine. The observable universe is just a patch, a window, a single view of something much, much larger. And dark energy, for all the destruction it promises, for all the galaxies it will eventually hide from view, also hints at the scale of what lies beyond. Because if the universe is accelerating everywhere, then everywhere must be very large indeed, larger than we can observe, larger than light can reach, possibly larger than infinity, and that is where we go next. We just watched dark energy tear the cosmos apart, slowly, inevitably, accelerating the expansion of space until distant galaxies slip over the horizon one by one, their light redshifted into invisibility, their futures forever cut off from ours. The observable universe shrinking in content even as it grows in radius, a bubble of visibility surrounded by darkness, 93 billion light-years across, 2 trillion galaxies, and all of it temporary, all of it fading as the expansion carries everything away faster than light can follow. That is the observable universe, the part we can see, the part from which light has had time to reach us in the 13.8 billion years since the Big Bang, a sphere centered on Earth extending roughly 46 billion light-years in every direction. The cosmic microwave background marking the edge, the oldest light, the farthest signal. Beyond that, nothing is visible, not because nothing is there, but because the light from anything farther away has not had time to complete the journey, or because the universe was opaque before the CMB formed and light could not travel freely. The observable universe is a horizon, a boundary, a limit imposed by the speed of light and the age of the cosmos. And it is not the universe. That phrase needs to be said plainly, because there is a tendency, a natural human instinct, to assume that what we can see is all there is, that the observable universe is the universe, that the boundary of our vision marks the edge of reality. It does not. The observable universe is just a patch, a window, a single view of something that almost certainly extends far beyond what we can ever hope to see. How far? That is the question. And the answer, depending on which model you trust and which measurements you believe, ranges from uncomfortably large to infinite. Let's start with what we know. The universe is flat, or very nearly so. That statement requires unpacking, because flatness in cosmology does not mean what it sounds like. It does not mean the universe is a disk. It does not mean space is two-dimensional. Flatness refers to the geometry of space itself, the curvature. General relativity tells us that space can bend. Mass and energy warp space-time. A massive object like the sun creates a dip in the fabric of space. That dip is what we experience as gravity. On the largest scales, the total amount of mass and energy in the universe determines whether space curves back on itself like the surface of a sphere, curves outward like the surface of a saddle, or stays flat like an infinite sheet of paper. If the universe is positively curved like a sphere, then it is finite. You could, in principle, travel in a straight line and eventually return to where you started. The universe would loop back on itself. A closed universe. If the universe is negatively curved, like a saddle, then it is infinite. Space stretches forever in every direction. An open universe. If the universe is flat, then it is also infinite, or at least flatness is consistent with infinity. A flat universe extends forever with no curvature, no edge, no boundary, just space going on and on and on. Measurements from the cosmic microwave background, specifically from the Planck satellite and earlier missions like the Wilkinson Microwave Anisotropy Probe, have pinned down the curvature of the universe with extraordinary precision. The data says the universe is flat to within a fraction of a percent. If there is any curvature at all, it is so slight that we cannot detect it. The most recent measurements put the curvature parameter, called omega, at 1.000 plus or minus about 0.4%. 1.000 is perfectly flat. The error bars are tiny. The universe appears to be spatially flat, or so close to flat that the difference does not matter for most purposes. And if the universe is flat, then it is almost certainly infinite, not definitely. Flatness allows for the possibility of a finite universe if space wraps around in some clever way that we have not detected. A flat torus, for example, could be finite but have no curvature. But the simplest interpretation, the one that requires the fewest assumptions, is that a flat universe is infinite. Space extends forever. There is no edge, no boundary, no place where the universe stops and something else begins. Just more space, more galaxies, more stars, more everything, forever. That conclusion makes a lot of people uncomfortable. Infinity is not a number the human brain can process. It is not even really a concept you can hold in your head for more than a few seconds before it starts to slip away. An infinite universe means there is no center, no special location. Every point is equivalent to every other point. The Milky Way is not in the middle. It is not near the edge because there is no edge. It is just somewhere in an infinite expanse of space that looks roughly the same in every direction as far as you can see and keeps looking the same forever beyond the horizon. An infinite universe also means there are an infinite number of galaxies, an infinite number of stars, an infinite number of planets, an infinite number of places where life might exist. And if the universe is truly infinite, then anything that is possible, no matter how unlikely, happens an infinite number of times. Somewhere out there, far beyond the observable horizon, there is another galaxy that looks exactly like the Milky Way. Another solar system that looks exactly like ours. Another Earth. Another you. Reading this exact script, the probability of that happening is unimaginably small. So small, it might as well be zero in any finite region of space. But in an infinite universe, it happens, not once, infinitely many times. That is what infinity means, and it is deeply unsettling. But infinity is just one possibility. The other possibility is that the universe is finite, very large, vastly larger than the observable universe, but not infinite, bounded, limited, just so big that we cannot see the boundaries from here. In 2011, a team of cosmologists led by Miran Vardanyan at the University of Oxford published a Bayesian analysis of the cosmic microwave background data. They were trying to pin down the size of the universe by looking at patterns in the CMB. If the universe is finite and smaller than a certain size, then the largest wavelengths of fluctuation in the CMB would be suppressed. You cannot fit a wave longer than the universe itself. So by looking at which wavelengths are present and which are missing, you can, in principle, set a lower limit on how large the universe must be. Their analysis found that the universe is at least 250 times larger than the observable universe. Some coverage of that result described the bound as roughly 398 Hubble volumes. A Hubble volume is another way of talking about the observable universe. It is the volume of space from which light has had time to reach an observer. So 398 Hubble volumes means the universe contains at least 398 separate regions, the size of our entire observable cosmos. Each one potentially filled with its own 2 trillion galaxies. Each one as vast and complex as everything we can see, and all of it sitting beyond our horizon. Invisible, unreachable, but real. 250 times larger than the observable universe translates to a minimum diameter of roughly 7 trillion light-years. That is the lower bound. The smallest the universe could possibly be and still be consistent with what we observe in the CMB. It could be larger, much larger. The data does not rule out infinity. It just says that if the universe is finite, it is at least 7 trillion light-years across, probably more. The 250 number is conservative, a minimum, not a best estimate. The true size could be thousands of times larger, millions of times. Or it could be infinite, and the question of size becomes meaningless. Let that scale sit for a moment. The observable universe is 93 billion light-years across, already incomprehensibly large, already containing 2 trillion galaxies, already so vast that the Milky Way becomes invisible when you zoom out far enough. And that observable universe, that entire bubble of everything we can ever hope to see, might represent less than 1/400th of the total. 1 pixel in an image with 400 pixels. 1 room in a house with 400 rooms. 1 galaxy worth of visibility in a cosmos with tens or hundreds of thousands of observable universe-sized regions, each one potentially as full as ours, each one containing its own cosmic web, its own clusters and superclusters, its own 2 trillion galaxies or more, and all of it beyond the light barrier, beyond the cosmic microwave background, beyond the reach of any telescope we could ever build. Here is what that means. If the universe is 250 times larger than the observable universe, then there are galaxies out there, trillions of them, whose light will never reach us, not because the light is too faint, not because it has not had enough time yet, but because the space between us and them is expanding so fast that the light will never complete the journey. Those galaxies are over the cosmic event horizon, permanently. They exist. They are out there right now. Stars are forming, planets are orbiting, chemistry is happening, maybe life, maybe intelligence, maybe civilizations looking up at their own night sky and wondering if they are alone. And we will never know. We will never see them. We will never communicate with them. They are part of the same universe, subject to the same physical laws, made of the same matter, but they are cut off from us, isolated, separated by so much expanding space that no signal, no message, no information of any kind can ever cross the gap. The same is true in reverse. There are civilizations out there, if they exist, who cannot see us, whose observable universe does not overlap with ours, who live in a completely different bubble of visibility. They look up and see their own cosmic web, their own clusters and galaxies and stars, none of which we will ever see. And they look out toward where we are and see nothing, not because we are not there, but because our light has not reached them and never will. The universe is full of isolated bubbles, overlapping in some places, separated in others, each observer sitting at the center of their own horizon, each one seeing a different patch of the same infinite or near-infinite cosmos. If the universe is finite, even if it is only 250 times larger than the observable universe, then it contains at least 500 trillion galaxies. Multiply 2 trillion by 250, 500 trillion separate islands of stars, most of them invisible to us. Most of them sitting in regions of space from which light has not had time to reach Earth. And if the universe is larger than the minimum, if it is 1,000 times the size of the observable universe, or 10,000 times, or 1,000,000 times, then the number of galaxies grows proportionally. 1,000,000 times larger means 2 quadrillion galaxies, 2,000 trillion. A number so large it stops having meaning, and all of it real, all of it out there, all of it invisible. If the universe is infinite, the count becomes meaningless. Infinite galaxies, infinite stars, infinite planets, infinite possibilities, and somewhere in that infinity, every possible configuration of matter plays out, not just once, infinitely many times. The math is uncomfortable, but unavoidable. In an infinite universe, the Milky Way is not unique. There are an infinite number of galaxies that look exactly like it. An infinite number of solar systems identical to ours. An infinite number of Earths. An infinite number of you. Not similar, identical, atom for atom, thought for thought. Every choice you have ever made, someone else has made the same choice in exactly the same way an infinite number of times. Every version of your life that could possibly exist does exist somewhere in an infinite cosmos. That is not philosophy. That is not speculation. That is the straightforward implication of infinity combined with a finite number of ways to arrange matter. If the universe is infinite and matter is finite in its configurations, then every configuration repeats infinitely. Most physicists are cautious about pushing that conclusion too far. Yes, the math says it is possible, but possible and actual are different things. An infinite universe allows for infinite repetition. It does not guarantee it. The distribution of matter might not be uniform. Some regions might be denser than others. Some regions might be empty. The cosmic web might look different in different parts of the universe. The laws of physics are the same everywhere as far as we can tell. But the initial conditions, the fluctuations in density that seeded galaxy formation, might vary in ways we do not understand. So while an infinite universe makes exact copies of Earth theoretically possible, it does not make them certain. The honest answer is we do not know. We cannot know. Those regions are beyond our horizon. We will never observe them. We will never test the hypothesis. It remains a thought experiment, a consequence of infinity that we can calculate but never confirm. here is the part that should bother you. We will never know how big the universe truly is, not with certainty. We can measure the curvature of space within the observable universe. We can set lower bounds on the total size based on patterns in the CMB. We can build models that predict inflation stretched the cosmos far beyond what we can see. But we cannot observe the whole thing. By definition, anything beyond the observable universe is unobservable. The light has not reached us. The information has not crossed the horizon. And because the expansion is accelerating, because dark energy is pushing space apart faster and faster, the amount of the universe we can see is shrinking. Not in radius, in content. Distant galaxies are slipping over the cosmic event horizon. Their future light will never reach us. The observable universe is becoming a smaller and smaller fraction of the total with every passing moment. If the universe is infinite, then the fraction of it we can see is exactly zero. Not approximately zero. Exactly zero. An infinite universe means the observable universe, no matter how large it is, represents 0% of the total. 93 billion light-years across. 2 trillion galaxies. All of human history and knowledge and exploration confined to a bubble that is literally 0% of the whole. If the universe is finite but very large, say 250 times the size of the observable universe, then we can see about 0.4%, less than half of 1%. If the universe is 1,000 times larger, we see 0.1%, 1/10 of 1%. The bigger the universe gets, the smaller our visible fraction becomes. And if dark energy keeps accelerating the expansion, that fraction will keep shrinking forever. There is no way to escape this conclusion. The observable universe is a horizon, a boundary set by the speed of light and the age of the cosmos, and that boundary does not mark the edge of reality. It marks the edge of what we can see. The universe extends beyond it. How far, we do not know. Possibly forever. Possibly just incomprehensibly far, but definitely beyond. And we are stuck inside our bubble, unable to see out, unable to reach the other regions, unable to test whether the universe is finite or infinite, unable to count the total number of galaxies, unable to map the full cosmic web. We can see our patch, and that is all we will ever see. NASA describes this situation plainly. The observable universe is everything within a certain distance from Earth, but the universe as a whole may be much larger or infinite. The distinction matters because it changes what the word universe even means. If the universe is everything that exists, then it includes all the regions we cannot see, all the galaxies beyond the horizon, all the space that has not had time to send us light. The universe is bigger than the observable universe. How much bigger is unknown, but the fact that it is bigger is almost certain. The cosmological principle says the universe should look roughly the same everywhere. No special locations, no center, no edge. Homogeneous and isotropic at the largest scales. That principle has been tested within the observable universe, and it holds. The cosmic web looks the same in every direction we look. The distribution of galaxies is uniform when you average over large enough volumes. The CMB is the same temperature in every direction to within 1 part in 100,000. The observable universe is homogeneous. And if the observable universe is representative of the whole, then the whole universe should also be homogeneous, which means the regions beyond our horizon should look like the regions inside it. More cosmic web, more filaments and voids, more clusters and superclusters, more galaxies, the same structure repeating over and over across distances we will never measure, but we cannot prove that. We can only assume it. The cosmological principle is an assumption, a well-tested assumption within the observable universe, but an assumption nonetheless when applied to regions we cannot see. It is possible the universe beyond our horizon is different, radically different. Maybe the density is higher, maybe the density is lower, maybe there are regions where galaxies never formed. Maybe there are regions where galaxy formation happened faster and the structures are more advanced. Maybe the laws of physics are different far enough out, though that seems unlikely given how tightly constrained they are by the CMB and other observations. We assume the universe is homogeneous everywhere because it is homogeneous here, but we do not know, we cannot know. The evidence is beyond the horizon. Here is the thought that keeps cosmologists awake. If the universe is infinite, or even just vastly larger than the observable universe, then everything we have learned about cosmology, every measurement we have made, every model we have built, is based on a sample size that represents 0% of the total. We are extrapolating from one patch to the whole, assuming that what we see here is representative of what exists everywhere. That assumption might be correct. The cosmological principle might hold across infinite space, but it might not, and we would never know. The universe could be wildly inhomogeneous at scales larger than the observable universe. It could have structure we cannot detect, patterns we cannot see, variations in density or temperature or expansion rate that only show up when you zoom out far enough. And if that is true, then all of our models are wrong. Not wrong in detail, wrong in scope. We would be describing one small region and calling it the universe, like an ant on a beach, declaring that all of reality is sand because sand is all it can see. That is the uncomfortable position we are in. We have mapped the observable universe. We have counted the galaxies. We have traced the cosmic web. We have measured the expansion. We have discovered dark energy. And all of that work, all of that data, all of those conclusions might apply only to our local bubble, the part we can see, the part that might be a tiny, tiny fraction of the whole, or 0% if the universe is infinite. We are trapped inside a horizon we can never cross, looking out at a cosmos that extends far beyond what we can observe, and we have no way to know how far. Let's bring this back to scale, back to where we started. You live on Earth, a planet roughly 12,700 kilometers across. Earth orbits the Sun. The Sun is one of 400 billion stars in the Milky Way. The Milky Way is one of about 50 galaxies in the local group. The local group is one of many groups in the Virgo supercluster. The Virgo supercluster is part of Laniakea, which contains about 100,000 galaxies spread across 400 million light-years. Laniakea is one supercluster among thousands in the observable universe. The observable universe contains roughly 2 trillion galaxies spread across 93 billion light-years, and the observable universe might represent less than 1/400th of the total cosmos. Possibly much less. Possibly 0% if the universe is infinite. You are living on a rock orbiting a star in a galaxy that is invisible when you zoom out far enough. That galaxy is part of a supercluster that is invisible when you zoom out farther. That supercluster is part of an observable universe that might be invisible when you zoom out to the scale of the true universe. The hierarchy does not stop. Every time we zoom out, the previous scale becomes insignificant, and we have now reached a scale where we cannot zoom out anymore. Not because we have reached the edge, but because we have reached the edge of what we can see. The universe might keep going, probably does keep going. But we are stuck here, inside our bubble, looking out at a boundary we can never cross. The Milky Way is not small. It is enormous by human standards, 100,000 light-years across, 400 billion stars, more mass than 1 trillion suns. It has been rotating and evolving for more than 13 billion years. It is a vast, ancient, complex structure, and it is nothing. One galaxy among 2 trillion in the observable universe, one thread in the cosmic web, one pixel in a map that might extend 250 times farther in every direction, or 1,000 times, or infinitely. The Milky Way is a speck, a grain of sand on a beach that stretches farther than we can measure. And that beach might be one beach among infinite beaches in a cosmos so large that the word large stops having meaning. Here is the final piece, the part that ties everything together. We are not special. Earth is not special. The Sun is not special. The Milky Way is not special. The local group is not special. Laniakea is not special. The observable universe is not special. We are one planet, in one solar system, in one galaxy, in one cluster, in one supercluster, in one observable bubble, in a universe that might be infinite. Every scale we measure, we find we are not at the center, not at the edge, not in a unique location, just somewhere, anywhere. A random point in an expanse so vast it defies comprehension. The Copernican principle, the idea that we do not occupy a special place in the cosmos, holds at every level. We are not the center of the solar system, the Sun is. We are not the center of the galaxy, a supermassive black hole is. We are not the center of the local group, Andromeda might be. We are not the center of the universe. There is no center, or every point is the center, depending on how you define it. The universe has no preferred location, no special region, no place that matters more than any other place. We are here. We could just as easily be anywhere else. And it would look roughly the same. That is the ultimate lesson of cosmology. The ultimate conclusion of mapping the universe at every scale. We are small, insignificant. A brief flicker of complexity in a cosmos that has been expanding for 13.8 billion years and will keep expanding for trillions more. The Earth will not last. The Sun will die. The Milky Way will merge with Andromeda and settle into a quiet elliptical galaxy. That galaxy will drift through space as the cosmic web dissolves and the universe expands into darkness. And through all of that, the vast majority of the cosmos, the part beyond our horizon, will continue on completely unaware that we ever existed. We cannot reach it. We cannot see it. We cannot affect it in any way. It is there, real, enormous, possibly infinite, and utterly indifferent to us. But here is the thing. We figured it out anyway. We measured the distances, we counted the galaxies, we traced the expansion, we discovered dark energy, we mapped the cosmic web, we pinned down the curvature of space, we set lower bounds on the size of the universe, even though we can never see most of it. We did all of that from one small planet orbiting one average star in one unremarkable galaxy. We pointed telescopes at the sky. We collected light that had been traveling for billions of years. We built models, we tested predictions, we refined our measurements, and we constructed a picture of the cosmos that is almost certainly correct within the observable universe and probably extends far beyond it. That is not nothing. That is remarkable. We are a species that has existed in its current form for maybe 300,000 years. We have had telescopes for 400 years. We have understood the expansion of the universe for less than a century, and in that brief span, we mapped the structure of everything we can see and began to grasp the scale of what we cannot. The universe does not care. It will keep expanding. Galaxies will keep slipping over the horizon. The observable cosmos will grow darker and emptier. In a few trillion years, the evidence of the Big Bang will be gone. The CMB will be undetectable. The distant galaxies will have faded. Future civilizations, if they exist, will have no way to discover what we discovered. They will live in a universe that looks static and empty. And they will be wrong, but they will have no data to correct them. We are living in a unique window, a brief period when the universe is old enough to have formed galaxies, but young enough that we can still see most of them. The cosmos is revealing itself, and we are here to witness it. That might be the closest thing to meaning the universe offers. Not that we are important, but that we are here, now, able to look, able to measure, able to understand, at least in part, the scale of what we are embedded in. The universe is at least 250 times larger than the observable universe, possibly much larger, possibly infinite. We will never know for certain. The data is beyond the horizon. But the fact that we can even ask the question, the fact that we can set limits and build models and glimpse the edges of something vastly larger than ourselves is worth something. It is worth the effort. The Milky Way is impossibly small compared to the cosmos. Earth is a speck on a speck. You are an arrangement of atoms that will last maybe 80 years on a planet that will last a few billion more in a galaxy that will drift alone through an ever-expanding universe until the last stars go dark. That is the scale. That is the truth. And somehow, against all odds, you are here, aware, conscious, able to look up at the night sky and wonder what lies beyond. Able to read about galaxies and clusters and superclusters and dark energy and the cosmic web. Able to grasp, even if only for a moment, that the universe is larger than you can see, larger than you can imagine, possibly larger than language can describe, and that you are part of it, a tiny part, an insignificant part, but a part nonetheless. Made of the same atoms, subject to the same laws, woven into the same web that stretches across billions of light years and possibly trillions more beyond the horizon. That is where we are, a speck within a speck within a speck. The Milky Way is one galaxy among 2 trillion. The observable universe might be one bubble among hundreds or thousands or infinitely many. And all of it, every galaxy, every star, every planet, every atom, is part of a cosmos so large that the word universe barely contains it. We do not know how big it truly is. We will never know. But we know it is bigger than we can see. And that knowledge, uncomfortable as it is the best answer we have. You live on a planet you cannot feel moving. You walk on ground that is screaming through space at hundreds of thousands of kilometers per hour, and you perceive none of it. The sun drags you around the galactic center once every 230 million years, and you have never noticed the ride. The Milky Way, vast and ancient and glowing with 400 billion suns, is falling toward Andromeda at 250,000 miles per hour. And to you, the sky looks still. That should tell you something about perspective, about scale, about the limits of human intuition when faced with a cosmos that operates at distances and timescales our species was never built to comprehend. We thought we lived in the universe. We were wrong. We live in a corner of a thread on a web that stretches 93 billion light-years across, 2 trillion galaxies, each one a world unto itself, each one containing billions or trillions of stars. And that entire observable cosmos, everything we have ever seen or ever will see, might represent less than 1% of what actually exists, possibly far less, possibly 0% if the universe is infinite. The Milky Way is not small, but it is nothing. A single galaxy among trillions in a structure so vast that light itself takes longer than civilizations last just to cross a fragment of it. You are standing on a rock in that galaxy. One planet among trillions, One life among billions on that planet. A brief arrangement of atoms that will last maybe 80 years in a cosmos that has been expanding for nearly 14 billion and will continue for trillions more. The scale is so large, it stops meaning anything, and yet here you are, alive, conscious, able to look up and ask how far it goes. Able to measure the distances, able to count the galaxies, able to glimpse, even if only for a moment, just how impossibly small we really are.